And that's taking notes. Cool. Okay. Still with the doors. I wasn't able to get to the PowerPoint today, so we're just gonna have to enjoy this beautiful blue screen and go from there. So sorry about it, but today was a busy day. I hit a deer last night, and so I was like, well, I gotta fix the car a little bit, and fixed it and enough, and so everything's good now. But yeah, my wife came into town. She was coming from Salt Lake actually last night, and she got in at 2 a.m. So it was a late night, but and then leave the house literally within a mile of my home. Boom, there goes a deer. Came back, switched vehicles, and then went picked her up. Everything. So just had to kind of clean up messes today, and I go on a trip tomorrow, so didn't have time to do much. So sorry about it, but this is a fine PowerPoint too. All right. We'll jump right into the electrical system of the CRJ 700. Uses both 115 volt AC alternating current and 28 volt DC direct current power. The primary source of the AC power is two engine-driven integrated drive generators, and constant speed drives turn the IDGs at constant RPM. This one actually hits a little closer to home. Just because the second to last flight that I did, it was from Chicago to South Bend, super short flight. You'd think, oh, what could go wrong? It's like 20 minutes of airtime. So really, really easy. Well, I actually lost engine 2 IDG. And so we're just sitting there cruising, and all of a sudden we get this caution message, and it's like, and the autopilot disconnects, and we are disconnected from mock trim and a yaw damper, and just that the hard exchange and going from 2 generators to 1 generator kicked a bunch of stuff off. Yeah, it wasn't super cool, but this goes back to the primary function of the APU, which is to back up the IDGs. And so before even, you're not supposed to do this, but I'm confessing my sins to you guys. When something like that happens, you go to the books. You just, okay, sweet, this is the message. Let me pull out the QRC, QRH, and go through the company's checklist, or the manufacturer's checklist on how to diagnose and fix this specific problem. But just from the understanding of systems and understanding of kind of what was going on, we were at a position where we're at 7,000 feet, so the APU can be started below, I believe, 30. And so we just started the APU, and the APU came on, and once we had that second generator, we were able to get everything back to normal, and then we ran through the checklist, and every single checklist that we ran through was like, start the APU, start the APU, start the APU. So it ended up being something that needed to be done at some point, but I should have followed exactly how it was written in that order, and I didn't. So there you go. I'm sorry. But yeah, so electrical key points: 115 volt AC, 28 volt DC. The DC power is limited to 5 minutes of use, so you can't have it on for more than 5 minutes before jumping back to. And that's just initially when you turn on. You turn on using DC power. We have a little checklist that we run, and then once we get that done, then we turn on the AC power, and the AC power will do its thing. It's the primary source of power that we use on the airplane. And the 2 IDGs are the source of that AC power. Constant speed drives, those are there just due to the fact that we always are using different power settings and thrust settings, and the engines are turning at different RPMs constantly. So these constant speed drives just take the RPMs of the engine, the rotations per minute, and they convert it into a constant RPM. So no matter if you're idle or if you're 90% thrust and you're taking off, the IDGs are going to continue to turn at a constant speed thanks to the constant speed drives. The APU provides an alternate source of AC power. ADG. Okay, so this is one of those things that you need to remember as well. So there's 4 sources of AC power. There's the 2 engine-driven integrated drive generators. There's the APU, and there's the ADG. ADG stands for air-driven generator. It's an emergency source of AC power. And what it is it deploys automatically when both main buses are without power and may be deployed manually. So yeah, pretty much when you lose all power to the airplane, let's say you lose literally both, like you have a terrible day and both your IDGs go out at the same time, your ADG will deploy. And the air-driven generator will obviously be only effective at a high speed. So pretty much it just looks like a little wind turbine, and it comes out the front right side of the airplane's nose, and it just drops down and hangs in the wind. And then as you're flying at 100, 200, sometimes 300 knots, just the airspeed will turn that air-driven generator, and it'll provide a source of AC power. Now that source, if you literally lose everything and that's the only source of power that you have, you need to be aware of that, because once you touch the ground and you start slowing down, once it stops spinning, it starts giving power and you're going to lose everything. So that's something that is talked about in the books that we have. And it just says pretty much let tower know, like, we are not going to be able to communicate with you once our airplane stops. So it's like, we're going to be on the runway. We're just going to stop. We'll need assistance immediately, and things like that. So yeah, the four you'll need to know is 4 things: 2 engine-driven integrated drive generators, and the APU and the ADG. And ADG deploys manually. Both main buses are without power. So buses are just like a set of circuits. So yeah, electricity kind of works where it's just you have a wire and the wire takes electricity to a specific part of the airplane. Well, in the flight deck, we'll see a ton of different circuit breakers, and they're all broken down into specific buses as well. So you can kind of imagine that like a bus is just taking 4 or 5 or 6 or 7 or sometimes 10 or 20 different circuits, and it puts them into the same category. And they do that so that if you have like an emergency failure or something like that, like the air-driven generator, it's not going to give AC power to the entire airplane. It's only going to give it to the essential things that we need on what we call the essential bus. Buses and the essential bus. Go ahead, Christopher.
Will one engine-driven generator power all the buses?
Yeah. Yeah, it can. It's annoying, but it also depends on the configuration of the airplane. If you have flaps greater than 0, it won't power everything. But if like the situation we ran into, when we were on 1 for a minute, the autopilot disengaged, the Mach trim disengaged, but that was reset. You just have to press it again. It's a button. You just press the Mach trim, and one of the yaw dampers disengaged. But after that, everything else still remained the same because we were clean. We didn't have any flaps out. Cool. I think I've hit that one on the head enough. The ADG power is distributed. So this is what we talked about. This is like the essential bus. It's to the flaps, slats, pitch trim, hydraulic pump 3A, and the AC essential bus. So yeah, the essential bus, just those essential items. I think only one of our radios will work, and I think the PFD, the primary flight display, and the multifunction display, so that what the pilots see, those only the left side will work. Only the captains will work. They kind of just dump everything that's additional and redundant just to say, hey, we got a problem. We got to get on the ground. And then pump 3B, hydraulic pump 3B is the other one that gets powered. DC power provided by 4 transformer rectifier units. And so those TRUs, they take AC power to DC power. And so we have 4 of them that convert that to the different electrical units that require DC power on the aircraft. And tunicates, batteries store and provide a source of DC electric power for normal and emergency operations. That's like starting the when we start the airplane initially. The first is the battery master. We turn that on, and the second we turn that on, we're running on DC power for a short amount of time while we do a few checklists and check the loads and make sure that the DC powers can start the APU. Once those batteries can, if they have enough juice to start the APU, then we'll start the APU. And if we're plugged into an external source, then we'll just click the external source and go from there. Yeah, electrical. AC and DC power systems utilize power centers to manage power distribution. And AC power centers distribute AC electric power to 4 AC buses. So there's 4 AC buses. I think it's main 1, main 2, essential, and non-essential bus. I think actually those are the 4 names. DC power center distributes DC electrical power to 9 DC buses. Things you don't really need to know. Like, you don't really need to know much about it. The biggest things that you need to know with this one are the 4 sources of AC power. And I think that's it. Yeah, I think that's it. Go ahead, Christopher.
So for dispatcher specific stuff, we're worried about the MEL. Is there a slide coming up that talks about the MEL for all the like the engine driven generators and stuff?
Yeah, good question. So MELs and CDLs, you're kind of ahead of the game. That's all tomorrow's stuff. But yeah, so if you have something broken, you'll get an MEL and then you'll be required to follow the fine print on the MEL. Yes. Yeah, that's tomorrow. You're ahead of it. If you have still questions about MELs and stuff like that, talk to the instructor tomorrow. Because yeah, you guys, that's one thing that is like the reason we go over systems is so that you can understand it well enough to be able to apply MELs and CDLs. And as the instructor tomorrow is going to tell you, like, contradicting MELs, you need to understand what those are and things like that, and just make sure that the systems you're not MELing the same thing. And anyways, yeah, you'll get into that tomorrow. But that is the reason why we are going over systems, is just to help you understand MELs. Let's see, IDGs. Yeah, we can talk about that. Sure, we can talk about that. So the MEL restrictions generally associated with the IDG. In the aviation world and the industry, we always want to have redundancy, which just means that we want to have 2 systems doing the same thing that could potentially be doing the same thing, so that if we lose one, we still have a backup. That's why there are 2 pilots. So if we lose one, there's still a backup. With that being said, if you have an engine-driven or an integrated drive generator that is deferred, the MEL is going to require that you are running the pilots are running the APU so they can have that backup generator throughout the entire flight. And then you think, okay, well, if you're running the APU is just a small jet engine in the back of the airplane in a little compartment that has an exhaust, but it burns the same fuel. It's much less. It's like 100, or it's like 200 pounds an hour or something like that. But it's still burning fuel. So when you're looking at your dispatch and you're thinking, okay, the IDG is deferred. Well, that means that if it's an hour flight, our fuel burn is going to be 200 pounds more than if we had both IDGs, because now we have to run the APU as well. And then you have to look at, okay, well, max flight operation altitude, sometimes depending on the airplane and you can only fly to a specific altitude, and that could affect fuel burn as well. So yeah, those are just things to consider when you have like an APU that's deferred. Let's see. Yeah, that looks good. The system or the airplane has a logic for how it likes its AC power. So we have the funny way of saying it. You don't need to know this, but just how the airplane prefers its AC power is on side. So there's two buses, main bus 1, main bus 2. So on side. So bus 1 is going to be powered by the left IDG, and the bus bus 2 is going to be powered by the right IDG. And so it's on side, inside, cross side, outside. And if main bus 1, if the IDG 1 is not working, main bus 1 will go next to the APU. If the APU is not working, then it'll go cross side to IDG number 2. And then if that's not going, then it'll go to the outside source. So that's our fun mnemonic on how to remember what the priority and what our aircraft likes. It's type of electricity. Let's see. Yeah, cool. And then we talked about a little bit about the primary functions of the APU. First is to back up the IDGs, to have that additional source of AC power in case you lose one from Chicago to South Bend, which probably will never happen ever again. And then the other one is the APU actually is what we use to start the engines on the ground. So those are the two primary functions of the APU, with a secondary being electricity and air conditioning on the ground. So yeah, its primary is to back up the IDGs in flight, and then secondary is electricity and air conditioning on the ground. Okay, let's see. Let's go back here. And some things that you'll need to consider with a broken APU, depending on the month. If it's summer and there's a broken APU, then you'll want to make sure that the outstations will have like low pressure air. So it's just an air conditioning cart that can pump in cooler air into the airplane while we sit and board and deplane, just to help try to keep the cabin comfortable. You'll want to also want to ensure that they have a functioning ground power unit, or like the JetBridge Power works. I went the other day to 2 different stations, Nashville and Chicago. It was those 2. It was Nashville and Chicago. And I didn't have an APU, and neither of their JetBridge Power worked. And so like it initially did, and then it died. And so I would trust it. So it's okay, we can shut down the engine now that the airplane's on, because technically on regulations, it says that we can't let passengers deplane or or board without the airplane being on, just for lighting purposes and making sure that passengers can see where they're going. Thankfully, it was day and the windows were open, so everything was fine, and the flight attendants felt like it was okay for them to keep going, so they kept deplaning. But yeah, I trusted one, shut down the engine, and like 30 seconds later, the JetBridge Power failed. And so I called them. I said, we need a ground power unit, and we need it like 10 seconds ago. And so they brought one over, but that's something you just need to check. And it's on the pilot's notes that we are told that dispatchers check. So if we're taking an airplane to an outstation, it's our understanding that you guys have already reached out and have already confirmed that they have both a ground power unit or a source of AC power, as well as an air start or a huffer cart. Those are the two things that they need. And then, yeah, obviously, if you're taking a broken APU plane down to Tucson in July, it's probably not the best choice. Go ahead.
I work for Spirit Ops out of Orlando, and I can attest that in the summer it is horrible when we get those NOP APUs because the AC cars have a really hard time keeping up to keep the aircraft cool enough to board. It's a nightmare. And a lot of times dispatch, I mean, I'll try to do better when I work, but they usually don't call to let us know. We have to check the sticker detail email. And then sometimes ones that aren't on the email come in with an NOP APU, and it's like, oh no, but it's a pain.
Yeah, I'm sorry. That's cool. Down in Orlando. That's awesome. What made you want to jump over to the dispatch side?
I've always been kind of contemplating it. I went to college for aviation management, and I have my PPL. So I always thought dispatching sounded kind of cool. And I'm 23 now, so I was like, this is the perfect time.
Yeah.
Finally do it. Yeah.
Yeah, there you go. There you go. PIC age. Yeah, that's crazy. I actually didn't know that until just recently when I was teaching at probably 2 or 3 courses. I'm not a dispatcher, just so everybody knows. I've not taken any dispatch school. The amount of information you're going to know by the end of this school is going to be more than me regarding just specific dispatch things, and probably even like flight planning and stuff like that, just because I don't do it anymore. You guys get to do it on a regular basis. I just look over what was sent my way and give the thumbs up or the thumbs down. Yeah, and so I just learned that just recently. Holy cow, you can't be a dispatcher. So it's like everybody that is a dispatcher, it's always been their like second or their third kind of career move. Just because you can't get started at it right away. You can't do it at 18 years old. You have to wait until you're 23. So yeah, this is a great time. I'm glad you found it. You trying to work for Spirit?
I'm thinking of jumping ships. We're not doing too hot right now, so.
Okay, cool. Yeah, I can't blame you there. Sometimes I'll commute on Spirit flights because I'm based in Chicago. They don't have direct from Atlanta to Chicago, but I think I actually take them sometimes from Atlanta to Detroit if I start a trip in Detroit. Anyways, and every time I commute on Spirit, the pilots that are flying, they're all super cool, super nice people, and I just feel bad for the situation that you guys have. So yeah, I can't blame you. I can't blame you at all. Cool. Well, let's get back into it. AC and DC, cool. We're done with that. Any questions about the electrical system of the CRJ 700? Sounds good. We'll talk about the ECS, the environmental control system. This goes along with the air conditioning stuff. ECS provides regulated, conditioned air to the flight deck and passenger cabin. And this is one of my favorite parts about the ECS. 2 of them. The left one only comes to the pilots, and the right one supplies the entire rest of the airplane. So when it's really hot, it's a little less hot for us. And when it's really cold, it's a little less cold for us up front, which is great. But yeah, there's 2 of them, the right supplies. And the 700, the packs actually do a really good job. We kind of talked about this earlier, but we're not legally allowed to board without the aircraft being powered. There's a trip I had in, I think it was August or September. They reflowed me to do a Santa Fe turn from Denver, and we were late, but we were the fastest option for them. So instead of like putting it on someone else, they just said, okay, well, whenever you guys get done with your turn, still run over this plane and work this flight. And then you can pick up your trip after that. So they reflowed us. And we, gate agents don't always know the rules or follow the rules, I should say. And when I got to the airplane, I went first. I had my first officer do the walk around and shut the airplane down. I ran over to start the new one and start the boarding process because it was going to take a minute. Well, when I got there, the flight attendants were on board. They were both brand new flight attendants and had really no idea what was going on. I mean, they did, but they just, they don't really apply the rules. Like, oh, I think we're not allowed to do this. Well, yeah, you're not allowed to do that. Anyways, and every single passenger was on board the 700 in August in Denver, and they were all seated and they're all waiting for me and my first officer. And I was like, well, a little late, but so I kept my bag in the jet bridge and I started the APU right away. And everyone was hot. They were all hot. They were all upset. But within like 3 or 4 minutes, the packs on the 700 were able to cool the airplane down enough that everybody was comfortable. So it was just crazy to see how quickly that those work and how great they do actually work for the environment. But there was one other time I boarded an airplane, and this time it was in Montgomery, and the van driver was late to get us from the hotel, like 45 minutes late. And we get to the airport and every single passenger is in their seats on a dark airplane, bags stowed. Everybody's just sitting there literally waiting for the flight crew to show up. I get on, the flight attendants follow, and the captain follows after that. And we're like, well, welcome aboard, everybody. Sorry we weren't here to welcome you. You're not supposed to be here, but you're here. It is what it is. So, yeah, the gate agents, I think I went to Montgomery like a few days later after that, and there was a Delta representative that was monitoring everything that the gate agents were doing. So I think they got in trouble for that one. Let's see. The forward and aft cargo bays are pressurized. So yeah, we will travel with large animals in crates in cargo bays due to it being pressurized. Only the aft cargo bay is ventilated with conditioned air, and conditioned air from the packs is blended and filtered with filtered recirculated air to optimize ECS performance. Yeah, it's conditioned, but it doesn't condition it as well as it does the cabin. So it's not super great. But you will see in summer days they'll have some ramp personnel, and I don't know if you do this, Caitlin, but is the 320 is that cargo bay, is it air conditioned as well?
Yeah.
Okay, so do you ever, like, on a hot summer day, just in between flights or whatever, just sit in the cargo bay and chill
No,
out?
I'm not out on the ramp. I'm in the office, which has AC, thankfully. But
Okay. Yeah,
I'm
so
sure they do.
I know the ones that I'll be walking around and I'll look up. Oh, homeboy's just chilling. He's hanging out in the cargo bay, and I'm like, oh, I can't blame him. So it does an okay job, but not a great one. Recirculated air can be up to 30%, 4% of total airflow. Single pack operation. So this is going to come into effect when you see MELs and CDLs. So single pack operations. So if you have your right pack deferred or your left pack deferred, we're limited to flight level 310, and that's due to the packs. Not only do they provide air conditioning, but they also provide pressurization to the cabin. And that just helps everybody breathe pretty much. Like there's the same amount of oxygen at 34,000 feet in the atmosphere as there is at sea level. So you can technically have the same amount of access to the oxygen, but up at flight level 340, it's the air is so much thinner, and we're not able to get the oxygen that we need to be able to breathe and stay conscious. So the single pack operations limited flight level 310, they pretty much just say that above 310, the single pack pressurization capability is not good enough. So if you're at 31, this is when your dispatch mind should be going. You say, okay, well, at flight level 310, if I'm flying for 3 hours at 310, I am going to burn more fuel, and it might be not as strong of a tailwind or a stronger headwind than I want, and go from there. So yeah, you just have your dispatch mind be thinking and say, okay, well, what's the actual, what kind of things impact the single pack operation to flight level 310? And that's when you think about those things. Two dual channel system controllers monitor and control the air conditioning systems. This is actually an upgrade from the 200. And we have a page, the ECS page, and in the 200, it just shows you actual cabin temperature, but in the 700, it says actual in the flight deck and the cabin, and it also shows selected. So we have a knob that we can choose the temperature in degrees Celsius. So it's usually, I usually set like 23, 24. Nobody really complains if it's about there. And then it'll adjust the temperature for that. But for the 200, you just kind of have to guess. And then if it starts getting too hot, you just bring it down a little more. And if it starts getting too cold, you turn it up a little bit. And it's not as good as the 700. The 700 is super nice, super easy to maintain a comfortable cabin for the passengers. Okay, any questions with the air conditioning or any comments with air conditioning, ECS, 2 packs, 1 pack, single pack, any of those things? Cool. Make sure there's nothing on here that you need to know about. I think that's it. So, how do the air conditioning packs work? How many packs are installed in the aircraft? Air conditioning packs take the hot compressed bleed air from the engines. So it's like how the engine works is the intake air goes into the initial nacelle or opening or cowl of the engine, and then the blades that are designed in the engine will spin around and rotate and compress the air more and more and more. And then what the packs will do is they will take off of the 10th stage. So imagine you have like 10 rows of little blades that are all spinning separately, individually, or together. Just depends on how everything's running and how everything's built. But so count like 10 fans black. Every single fan, the air gets more and more and more and more compressed. And so once it gets to the 10th stage, it'll pull the there'll be a little valve that will be open, and it'll suck some air out of that engine from the 10th stage. So it'll be really hot, it'll be really pressurized, and it'll take it to the packs, and the packs will cool it down and then send it through the cabin for the passengers to breathe, as well as to get cooled down. They cool it using air cycle machines, which include heat exchangers and turbines, and then mix it with recirculated air to provide cooled conditioned air. And there are 2 packs. Cool. All right, back to this. We'll go to the next one. Fire and overheat protection. So the fire and overheat key points, we have two subsystems: the fire and overheat detect fire, overheat, or smoke conditions, and then the fire extinguishing, containment, and delivery of extinguishing agent to protected areas of the aircraft. So one detects it, one gets rid of it, or tries to get rid of it. And is controlled by the Fire Detection and Extinguishing Unit, the FIDEX. And okay, so the overheat areas of protection. So this is where all of everything is. So engines have overheat areas of protection, the APU, and the main landing gear. Smoke detection is just in the forward and aft cargo bays, and the lavatory has a ceiling mounted smoke detection. The engine fire and overheat protection detects fire and or overheat condition in the engine nacelle. Okay, two extinguishing bottles for engine fire. Both bottles can be charged into either engine. On the ground, APU shuts down automatically and discharges halon into the APU compartment. Okay, cool. Yeah, pretty much what's happening is they have loops, and the loops will detect heat. And how they detect heat is there's a continuous form of electrical current going through these loops. And as you know, if something heats up, electricity will flow faster through the loops than it would if it's just at normal temperature. So it's just continuously feeding electricity through these loops over and over and over and over again. And if it becomes an overheat scenario or situation, though the electricity is going to actually have less resistance, and it's able to detect the smallest change of resistance. So it'll detect that there's a little bit of a change of resistance due to there's a fire in the gear bays or things like that, and it'll respond accordingly. So they have detection in so those loops are in the main gear, they're in the engine nacelle as well as the APU compartment. However, and then the smoke detectors are we talked about, in the forward and aft cargo bays and then the lav. The main landing gear does not have a way for us to deploy a halon bottle into. We can't extinguish any fire in the main landing gear base. That's done by, depending on where you're at, by lowering the gear. If we're at a position where we can lower the gear, we can go slow enough to avoid breaking any aircraft limitations, then we'll drop the gear and then it'll slow it down, and then just the air will ideally extinguish the fire. The engine, we do have two bottles, and we have for each engine, and one can be deployed for each, or one can be deployed for both, or both can be deployed for one, etc. And then we have some in the APU as well, and the forward and aft cargo bays. So yeah, this one's kind of cool. Two extinguishing bottles for engine fire. Both can be discharged into either engine, which is sweet. On the ground, so this is an automatic feature that does not happen in the air. On the ground, the APU detects a fire in the APU bay. The APU shuts down automatically and discharges halon into the APU compartment when a fire condition detected. So whenever it senses it, boom, it just shuts it down and deploys the bottle without any questions. In the air, the APU shuts down automatically, but the crew must discharge the halon bottle when a fire condition is detected. So shut it down, won't make it worse. The APU is located in the tail section. I can actually, wait. I think I took a picture. Oh no, that was the 200. I'll show you. Standby one. Okay, we'll go here, there. Drive. I should have a good picture of it, but it doesn't look like I do. Sweet. Well, I'll pull this up. We can use our imaginations. Okay. The exhaust is, where's the little thing? There we go. Okay. So the exhaust comes out right here. That's where the exhaust is. And the intake is right there. And the APU is located right here. So it's all in this section. It's just a little compartment for it. So it goes in, does its thing, and then blows out right there. Does that answer your question? Hope so.
Yeah, yeah. Is that typical for most aircraft? Is it usually in the tail, or is it just dependent on where the engines are?
Yeah, most of them are in the tail. If you look at the pretty much the tail of any airplane, even I know that there's a 350 picture on this slideshow as well. Let's see if it shows the tail. Of course it doesn't. Why would it do that? No. Yeah, it doesn't. So, but yeah, even 737s, most of them, if you look at just the tail section, like that very end piece of the tail, most of them you can see there's an exhaust coming out of it there. So yeah, it's the majority of airplanes that I know of have them coming out of the tail. Triples do, 737s, 320s. And I mean, some have different locations, but the majority of them are in the tail.
Okay, cool. Thanks.
Yeah. Okay. Sweet. So yeah, APU, we have to shut off in the air, or we have to deploy the bottle in the air. On the ground, it does it automatically. And it should talk about the two different, there we go. Okay, so 2 cargo fire extinguishing bottles. This one's cool. One is for immediate discharge. So if smoke is detected, and the crew elects to blow the bottle, the first one just blows completely and just covers everything in the halon, the fire extinguishing gas, and just ideally just coats everything so that nothing else can catch on fire. And ideally, it also puts out the other fire. 2 of them will go off though. One for immediate discharge, and then the other one to discharge slowly for maintaining a halon concentration in the cargo bays. And does it tell you how long? Nope. 1 hour. In this 200, you had 45 minutes. In the CRJ 700, you now have 1 hour of time before that second bottle will fully discharge. So you have a little bit more of a window of, okay, if we're actually going to the destination, should I continue? Should I just get on the ground? Well, the fire's put out, smoke's no longer detected, the bottle is still pumping. Yeah, let's continue. Let's get to that hub or whatever. If we're going to Chicago, let's get to Chicago and let people in Chicago figure it out rather than make it a problem for someone in St. Louis or something like that. So, cool. That's the fire and overheat key points. Let me make sure. Does anybody have any questions about the fire and overheat detection system or the halon or anything like that? I don't think you need to know much about this one. So this one was just kind of a fun thing to learn. Yeah, you don't. Okay, cool. Next, flight controls. Okay, we love flight controls. Flight controls key points. The wing is advanced technology airfoil, manufactured as a single unit and bolted to the fuselage in 10 separate locations. And the primary flight controls consist of elevators, rudder, ailerons, and multifunction spoilerons. we talked a little bit about this yesterday, and it's a concept that Jade and I are still working through. But the CRJ 700, its primary flight control is one of its primary flight controls is the multifunction spoilerons. So elevators, those are in the back, they control pitch up and down. Rudder controls yaw, left and right, and the aileron controls roll. And the multifunction spoilerons also control roll. They have an alternative function of just being spoilers. So if you grab the spoiler lever and you pull them, the multifunction spoileron will deploy, but they're not acting as ailerons at the time. So those ones, it's a tricky one just for the purposes of this class. And the CRJ 700 know that these four are the primary flight controls. When you go talk to your CFI or whoever you're talking to, trying to get your next license or rating or whatever you got to do, most airplanes just have the three. The primary flight controls are just rudder, elevators, ailerons. With the CRJ 700, thanks to the multifunction spoilerons aiding in roll at low airspeeds, then they become a part of the primary flight control system. So we talked about it last class, and I told you, I was like, no, there's no way that they are. And then he changed some things, but not everything. And then I talked to him again. I was like, yeah, actually, when I read through the manuals and talked about this with some people that know much more about this airplane than I do, they classify them as primary due to the fact that they assist with roll at lower airspeeds. And he's like, well, that's annoying. So yeah, like I said, just remember that for the CRJ 700 and for your Cessna 150 or 172 or whatever, forget about it. Secondary flight controls. So the difference between primary and secondary, primary is like the bare bones. You have to have these to fly the airplane. Like you have to have them. And secondary, those are ones that I would look at as kind of convenience. It's really nice to have these, but you don't necessarily have to have them. So secondary flight controls, horizontal stabilizer trim, slats and flaps, multifunction spoilers, which is the same thing as the multifunction spoilerons. Just in this case, now we're just using them as just spoilers. Ground spoilers, aileron and rudder trim systems. So we talked about trim yesterday. Trim just releases the amount of force required on the flight crew to keep the aircraft in the position that they want it to. They can trim it out, and the trim will hold the airplane where they want it to. And then, so that's the horizontal stabilizer trim, rudder, aileron, and rudder trim. So that's like stab trim that controls pitch. Slats and flaps, that helps with maneuverability at low air speeds. Go ahead, Brian.
The ground spoilers, are those for landing? Like
Yeah.
thinking, there's
Yeah.
those things that flap up on top of the wing. Okay. Okay, cool.
Yeah. Those are activated when weight on wheels hit and the thrust levers are idle. So once those two things are happening, boom, those ground spoilers, all of them pop up. And yeah, you see them, you probably think that's weird. And then they deploy, and then when we pull the reversers, they do that. But then when we stow the reversers, and once we get below a specific airspeed, they'll set themselves gently back into the wing for next time.
So those activate automatically then? That's not something that you guys have to trigger when you land?
Correct. There's some so for the CRJ 700, we don't do anything to activate those other than land the airplane and bring the thrust levers tight on, and that's it. I believe in the Airbus, they have to arm the ground spoilers. So if they don't arm them, they're not going to deploy. But it's a really easy thing. They just pull up on the spoiler lever, and then it's considered armed. And then once they land, they slow down, and then they do it themselves as well. So cool. Good question. All right. Let me see. Oh yeah, we can do a few more slides and then we'll go. Flight controls key points. In an extreme emergency, primary flight controls remain hydraulically powered by AC motor pump 3 Bravo. Now this is important because if you think back to the slide about the air-driven generator, so let's say you lose all AC power, boom, the ADG pops out. The air-driven generator powers hydraulic pump 3 Bravo, 3B. And in extreme emergencies, that would be an extreme emergency, primary flight controls remain hydraulically powered by AC motor pump 3B. So boom, you lose everything, ADG drops, 3B's powered, you still have your primary flight controls, which is huge. That's definitely something that we need. The PCUs, power control units, hydraulically move control services from mechanical inputs of the cockpit controls. All right. We'll talk a little bit more about the PCUs in a minute. And let's go ahead and take 15, 840. 840, come back, and we'll keep talking about the flight controls. If you have any questions, bring them back then. Thanks. All righty. Everybody, welcome back. We'll keep jumping into flight controls. This one actually turns out to be a little longer than I thought it was going to be, but all good information. The PCUs we just kind of briefly talked about. Power control units hydraulically move control surfaces from mechanical inputs of the cockpit controls. So pretty much how it works is the mechanical inputs, let's say I try to turn right. So boom, turn right. The mechanical input will go through wires down to a computer, which will trigger a hydraulic system to operate the ailerons and the multifunction spoilerons if we're moving at slower airspeeds. And then those will control. And when I go back to straight level, same thing. It'll go through a wire to a computer, tell the hydraulics, chill out, and it'll go back to normal. So those are the PCUs. If you pull apart like a Cessna or whatever, you'll look and you'll see there'll be a bunch of cables and pulleys and things like that, because the flight controls, literally as you move them, they move a cable, and the cable will move the actual surfaces. And there's other systems, but once you get to the airlines and the CRJ 700 and things like that, everything is controlled through a computer. So the input that we make goes to a computer that tells the hydraulics to move the controls. Okay. And this is what we talked about earlier. I should have waited to talk about it, but too late. Multifunction spoilerons operate on the downgoing wing only to assist the ailerons in roll control at lower speeds. That's what makes them primary flight controls. The CRJ 200 does not have this. A rudder travel limiter is installed to prevent pilot from overstressing the vertical stabilizer. RTL monitors the flat position, airspeed, weight on wheels, and the engine operation to limit rudder travel. I wish I had the story of this pulled up, but I'm just going to tell it to you. The reason that the rudder travel limiter came to be is because there was a American Airlines, I believe. It was an American Airlines flight that the first officer was fooling around doing something. I forget what exactly he was doing. Anyways, he pressed the rudder pedal to its full deflection. So at cruise, going 300 miles an hour or 300 knots, he pressed the rudder, full deflection, broke off the tail, and they ended up having some problems. I can't remember if they crashed or anything like that, but the rudder travel limiter is in place to specifically stop that from happening. So if you imagine, like, here's the full scale of the rudder, the faster you go, like the scale is full. So if you push it, like, this is how far it would go if you're not moving or you're going at slower airspeeds. However, the faster you go, there's like there's some lines that pop up that will actually restrict it to about this much of movement. So now if you're at cruise going 300 knots and you stomp the rudder, instead of it going all the way over, it just goes all the way to this little section, which will turn you a little bit, but it's not going to have enough force to break off the tail and give you a whole lot more problems than just a little turbulence and a little yaw in one direction or the other. So rudder travel limiter is awesome. It is not in the 200. It is in the 700 and the 900. So you'll have to know what that is. And actually, you don't need to know what that is. It's just cool. Yeah, you know what it is. And why we have it is because someone messed up one time. And now we have a new system for it. So and then we talked about the flaps. The flaps consist of one pair of inboard and outboard flaps. Just means there's two sections of the wing, one inboard and one outboard. They move kind of together as it comes back. The flap positions are 0 or up. What? Oh, that's right, because the slats are flaps 1. Okay. The flaps positions are 0, 8, 20, 30, and 45. 8 or 20 for takeoff, 45 for landing. something to note, if you're ever dispatching a flight and they send you a message, yo, engine failure, we got problems. And they tell us that we need to communicate. So it's like aviate, navigate, communicate. Those are like the three things that we do. So aviate, make sure we're flying the airplane, make sure we don't get slow, make sure we don't crash. First thing, fly the airplane, and then navigate, make sure we know where we're going, and then communicate and let ATC, let dispatch, let the company, let everybody know what our problem is once we've got those three things done. But with that being said, if you lose an engine, our protocol is to land with flaps 20, which will significantly increase the takeoff roll. One engine's thrust is not enough for the full amount of drag that flaps 45 give. Yes, it helps with lift, but also really increases the drag, and it's just one engine's not enough for it to keep up. So we land at flaps 20, which will increase our approach speed, which will increase the landing roll, which will increase the requirement for a longer runway. So when you hear people say, oh, yeah, we need the longest runway available, you know, and in Denver, sometimes I think their longest one's like 16,000 feet. And you got this little CRJ going 150 knots coming into land with single engine on this 16,000 foot runway when they could have easily used the 14,000 or the 12,000 or the other ones over there. But just having as much room as you can is super important when it comes to emergencies, and when you're landing with flaps 0 or flaps at 20 or and then 45 is easy though. 45 is not a big deal, but if it's 20 or less, then yeah, that's a big deal. Leading edge slats are installed and consist of 3 panels on each wing. It's just broken into sections as the wing curves and does its thing. There's 3 sections of slats. The inboard slat is the largest. The outboard is the smallest. When required, slats are anti-iced with engine bleed air. We talked a little bit about bleed air. That's like I told you, like the 10-stage bleed air. So as the air gets compressed, the further back it gets in the engine, it gets kind of taken away and used for other things like air conditioning and things like that. Well, it also gets used for anti-ice and to go to the wings and to the engine cowls to heat the leading surfaces. That way we can keep the ice off of the wing. Slat positions are 20 or 25 degrees, depending on the flaps setting. Yeah, I believe the initial, so when you select the flap/slats selection to slats 1, it goes to 20. And then when you go flaps 8, it stays. And then when you get to flaps 20, I believe is when it goes to 25 degrees. So you have to get through like 3 notches to get the full amount of slats. Slats extend before the flaps, then retract after the flaps. Slats and flaps are electrically operated, and yeah, they're electrically operated. So the AC system will spin a motor that does something, and the flaps go, and the slats come out, things like that. Inboard spoilers work with the multifunction spoilers in operation of the ground lift dumping system. And that's, yeah, it's talking about the spoilers. And the ground lift dumping system is when wheels hit, thrust levers are idle, they'll pop up and help dump, lift, and slow down. Yeah, that's all that is. It's just ground lift dumping systems. A lot of people say, well, it helps you slow down. Well, no, really, it helps you dump lift. And in dumping lift, the drag increase will help you slow down. Okay, flight instruments, EFIS. EFIS is my favorite thing. I hate EFIS. EFIS, Electronic Flight Instrument System, consists of 4 electronic flight displays. Each pilot has a primary flight display and a multifunctional display, a PFD and a MFD. So those are the 4. So 2 PFDs, 2 MFDs equals 4 EFIS. And the primary display data is airspeed, Mach, vertical speed, altitude, attitude, heading, flight director command bars, navigation information, and autopilot information. Let me see if I can pull up something to help you see. I can show you exactly what we see on here. Yep. Where'd it go? I lost it. Okay, we'll share this tab. Okay, so this is kind of what we see. This is a PFD. So the pink command bars, that's our flight director. So pretty much what you ever set in your whatever the autopilot or whatever mode you want. When that's selected, this will actually tell you how to achieve what you've selected. Over here on the left is your airspeed indicator. You can see that they've got bugged. This little thing, this is what you can bug. They've bugged 252 knots. So that's your airspeed indicator. And then this is your altitude tape. They're at 36,000. They've selected 37,000, meaning that they're trying to climb. And then down here this is the heading that they've selected, which doesn't show up on this page, but it would show up on the MFD. And the actual number, it's like, I mean, if you look at it, you can count to see what it is. There's 160, 166 or something like that. This is your vertical speed indicator telling you how quickly you're climbing or descending. And this is your altimeter. This is in the wrong, we usually use, it'll look like 2909 or 2 is what it should read. But this is just another unit that they use. And then this is kind of this white arrow with this bar section right here in the middle. That's our course deviation indicator. If it's on center, right on the middle, right up and down, then you know you're centered on course. But if you imagine this white bar to be like here, that would mean that you're deviating from your course quite a bit. So that's what the PFD looks like. Up here, it shows the different modes that are selected. And this one doesn't really make sense because they're cruising and they have the localizer and the altitude captured. Well, actually, that does make sense. So if it's ALT, that means that it's captured on 36,000. If it was ALTS, it means that it's captured on the altitude, but that's also the same altitude that you have bugged. So ALTS, out selected, and then ALT is just altitude. Cool. Yeah, it's more stuff that you need to know, but figured it'd be nice for you to just see what we get to look at every day. Oh, I guess I could also show you what. Yeah, just a little bit more about this. So right here, this is telling us this little rectangle part right underneath the triangle. That tells us if we're coordinated in flight. So if we weren't coordinated, this rectangle would be displaced over to the left or over to the right. And this right now is saying wings are level. If this little triangle is pointed over at this one, that would mean that we're in a 30-degree bank. That's 45. If you get past 45, this plane starts to yell at you. They'll say bank angle, bank angle. And then that's 60 degrees. And obviously down there is 90, which you're never going to turn. I'll never turn a CRJ 90 degrees. Just because there's no reason to. We try to provide a smooth ride rather than a fun ride. Okay, we'll stop with that one. So that's PFD. The MFD, I'm not going to show you. It's got so many different things to to look at. There's so many different screens. You can see the fuel system, you can see the hydraulics, the electrics, the ECS, the anti-ice. There's like everything pops up on actually that's the engine display, so never mind, I lied. That one just shows like the moving map. It shows targets, it shows waypoints, it shows airports, and kind of whatever you want to select. So everyone will look different just depending on what the pilot chooses to select with that one. Okay, so let's see, we went over pretty much most of that. Airspeed, vertical speed, altitude, attitude, heading, flight director command bars, that's what we were talking about, navigation information, and autopilot information. That's 50. MFD shows HSI, FMS map, TCAS radar. So flight management system map, HSI horizontal situation indicator, and TCAS terrain or traffic collision avoidance system, as well as radar, so we can kind of paint the thunderstorms in front of us, figure out which route we can take to avoid the majority of the bumps. Some clouds are friendly. I'll look at, like we'll be cruising, and a lot of times I just try to stay in the clear air, because if you don't have to go through a cloud, I'll ask for a deviation. Hey, can I deviate 5 degrees right to just avoid this specific buildup? But some clouds look friendly, and so I'll just be like, that looks like a friendly cloud. Through it. And the majority of the times it is a friendly cloud, but I've been wrong. It has been a violent cloud before. Sometimes, like when we're close to the airport and everybody is following the routes the ATC has asked you to fly, you can't avoid them. But when you're up at cruise, it's really easy for us just to say, hey, we're looking to deviate 5 degrees right for buildup. And center will be like, deviations up to 10 degrees right, of course, are approved. I actually haven't done this since, but my second trip ever in the airline, so I had like 6 hours total in the CRJ. The Czech airman I was flying with, he sent a message to the dispatcher saying, hey, this is our course. How does it look getting through this section of thunderstorms? Because there was one kind of off to the left and one to the right, and we were kind of diving right through the middle of them. And he sent a message, and the dispatcher went over, looked at it, looked at the moving map, and thought, okay, well, they're going to be at this section in 15 minutes, which looks like it should be right where they want to be. And he said back, yeah, maybe 2 or 3 degrees more right, of course, would be okay and be a little better. But overall, your position looks good. So you might get those messages, and just know that we're staring at our radar, but our radar doesn't tell us as much as your radar does. And radar's not perfect either. There's a bunch of flaws with it. And so it's always nice to get a second opinion, and you guys can see our position. You can see kind of the course that we're heading on and how the weather's moving. So you have more access to information than we do when it comes to those kind of things. But yeah, we'll reach out, like, hey, what do you see? Does it look bad for you too? And you'll probably be like, looks bad, and we'll move forward. So that is the multifunction display. And we got 2 air data computers which calculate pressure, altitude, static air temperature, total air temperature, ISA deviation, vertical speed, indicated airspeed, Mach number, true airspeed, other system parameters. You don't need to know much about that. If you have any questions with it, let me know. But you just got to know, we got 2 computers that calculate a whole bunch of stuff that we use. And, you know, a lot of times if we're reporting ice or something like that to ATC, they'll ask for our temperature, and that will actually be the static air temperature, which just means still. Static is like still. Good.
You need both operating when you take off to fly into RSVN or RVSN airspace.
It kind of came in a little broken. RVSM, what was the second?
Do you need both air data computers operative, or can you go with one?
I believe both are required to be operative. I'm not sure the specificity on the air data computers. I know other things, but I'll write that down and I'll get back to you after break. Air data computer requirements. Yep, I'll look into that. I mean, I know that like you have to have an autopilot. Your altimeters have to be indicating within like 75 feet of each other. So at that point, yeah, pressure altitude, that's our altimeter. So that, yeah, I would say yes. Both of them would need to be working, and they would also both need to be reporting to a specific degree. And if they're not, then we're not allowed to operate in RVSM.
Okay, yeah, obviously a huge limitation if you can't go above 280.
Yeah, huge. Yeah, it's not cool. I remember doing a flight from Atlanta to South Bend. No, Appleton, Wisconsin. No autopilot from Atlanta to Appleton, and yeah, we were at 28, having way more fuel than we should have. But yeah, it's just due to the fact that we can't go into RVSM. I think that we might talk about RVSM, but for those that don't know about it, it's reduced vertical separation monitoring. It's pretty much a section of the air that ATC says, okay, only specific planes can go here when they're working the right way. That way we can, because the demand is so high, initially we'd have to have them separated by more. But in this section, if they're reporting right and they're doing good and they're good airplanes, then we can put them closer together, allowing more aircraft to take care of or to take advantage of the fuel saving opportunity and the tailwinds and things like that. So that's what RVSM is. The AHRS, Attitude, Heading, and Reference System. The CRJ 700's AHRS is frustrating, and that's why I say I don't like EFIS. Is we get this message that comes up a lot. It's called EFIS Comp Mon, and it's a heading flag when the heading of the captain is his PFD is off from the heading of the first officer's MFD by 6 degrees or more due to magnetic disturbances. So you park next to a jet bridge, or you taxi over an area that they put way too much rebar in, or things like that. Then we'll get this caution, ding, EFIS Comp Mon, and it just pretty much tells you that, hey, your headings don't match up. There's other failures with that specific EFIS Comp Mon, but when it's associated with a heading flag, which 99.9% of time in the CRJ it is, then you just look at the headings. You look at your compass, figure out which heading is the right one, and then either turn off the magnetic feature and then turn it back on, and it should snap to the right heading. Or there's like a little button, you can manually adjust the heading to meet it, and then if it matches up on the next turn or things like that, then you're good. But if it doesn't match up on the next turn, then you got more problems. So the gyro reference system that generates angular rate and linear acceleration information about the aircraft body axis, combined with the heading data and the flux deflector, provides highly accurate 3-axis AHRS info. AHRS consists of 2 computers, 2 flux detector units, and 2 compensator units. You don't need to know much about this. Just know that we have something that tells us our heading, attitude, and reference system, the AHRS. So you don't need to know much about it. Standby flight instruments. The self-contained integrated standby indicator. This one, it tells everything. It tells airspeed, it tells altitude, it tells you in Mach if you want that. It has an altimeter setting. Depending on the ISI you have, it'll also capture and follow a localizer and a glide path, but it's all backup information. It provides backup attitude, altitude, airspeed, and magnetic compass information. So it's all backup. And like I said, some also display the localizer and the glide slope data. When you're shooting an approach, if both your screens fail, but it's, you know, the weather's bad that you have to get down to see something, we can actually, I have not personally done it, but I know they used to train us on shooting an approach with just the ISI, the integrated standby indicator. But I mean, I don't think I've had a flight control or a flight display failure, a primary flight display failure ever. It's always worked really well. But I mean, they do happen, like the multifunctional displays, they will fail actually relatively frequently. On our FMS map page, if we have it zoomed too far out, we can go out to 320 miles where it picks up a lot of airports, traffic, etc. The screen will start to blink at you. And that's how you know you've gone too far. You need to limit the window and take it down to 160 or an 80-mile ring or 40-mile ring. Or anyways, if you don't do that soon enough, the screen will go black on you. And you have to wait till you get on the ground, and then you have to write the airplane up, and they come out and they unplug it and they plug it back in and say you're good to go. So it's kind of just an annoying thing. Or when you do like in the 200, when we transfer the generators over from the engines to the APU, the screens turn off for a second, turn back on. That's like less than half a second. And that'll sometimes trigger it to come back on. Fuel. Okay, fuel tank system. We got 3 tanks, left wing, right wing, and center tank with a single point of refueling. Fuel supplied to engines flows through collector tanks. Fuel is heated by a high temperature engine oil passing through a heat exchanger. Okay, so a point I want to make with this, it says single point refueling. That's for pressure refueling. So on the right wing, the first officer's wing, right as it connects to the fuselage, there's a panel where the fueler can plug into and also can control how much fuel he wants to go into the airplane. There are times where the auto cross flow valve is not working, and that just pretty much means that even though he's filling up only into the right side of the airplane, there's fuel going into both wing tanks. It doesn't go into the center tank until the wing tanks are full, so the fuel will go into those wing tanks. Well, if the cross flow valve isn't working, then they have to do what's called gravity fueling, and that has a different fuel number, max fuel that you can have. So, and usually in the CRJ 700, if you remember, we talked about it yesterday, but or maybe the day before. Anyways, it's 19,594 pounds of fuel for gravity, or no, for pressure refueling. And so that just means that they literally plug it in, and then the pressure fills up every single spot that it can of the fuel. But if you fill it from the top of the wing, you're not able to quite get the fuel out to the upper sections of the wing and the wing tanks. And so you're not able to get as much fuel in the wing tanks as you would have been if you were able to just use the pressure fueling opportunity. And why that matters? Well, if you're going from, like for me, the longest flight I've done in a CRJ is from Chicago to Boise, Idaho. And I think our release fuel was 16,000 pounds of fuel. I believe, if I remember correctly, I got to look it up. I'll type this down too. Gravity fuel number. But I believe that the gravity fuel number was actually, like, we couldn't have gotten 16,000 pounds of fuel into the airplane if the auto cross flow valve was deferred. So there, it has happened before, and it's something that the fuelers really hate because they have to go to one side, climb up on the wing, open the wing tanks, put up to 2,500 pounds more than the other side. And then once they hit the 2,500 pounds, they have to stop, take the truck around, get on the other wing, do the same thing. Now they can put 5,000 pounds in because they go equal up to 25 and then 2,500 pounds more. And then they have to go back to the other wing and then do the same thing on that wing to make it so that they're even on both sides. And it's one of the most painful things to do. Go ahead, Christopher.
How much of a ground delay did that cause? I mean, is it significant?
Not too bad. It depends. If the fueler's there right when we show up to the gate with all the passengers on board, it would take him less time to fill up the wings than it would for all the passengers to get off and all the passengers to get back on. So it shouldn't be anything too long. But now if you're going to a spot where it's a repo and you're empty and you go just to pick up passengers, then yeah, you might be looking at a little bit of a delay. If it's a shorter flight and you don't need as much fuel, a smaller amount of time. But if you're doing Chicago to Boise and you got 16,000, you got to do that like 4 or 5 times. So that one is where you'd have the more lengthy delays and things like that. So not too bad, but it's more just a headache for the fueler. You just kind of feel bad for them and say, sorry guys, plane sucks. Cool. So that's, it was just an emphasis on the single point refueling. Technically there are 3 points: the pressure and then the 2 gravities on top of the wings. Okay, fuel supplied to the engines flows through the collector tanks. So it goes from the wing tanks, pumped in to a collector tank, which flows into the engine. Fuel is heated by a high temperature. I talked about that. The engines in the APU have separate fuel distribution systems. Engine fuel flows from the collector tanks utilizing motive flow and main ejectors. DC boost pumps are used to move fuel during engine start. The APU fuel flows from the left collector tank utilizing DC electric fuel pump. Okay, so motive flow. Engine fuel flows from the collector tanks utilizing motive flow. We talked a little bit about, and this is going back to principles of flight, when we talked about air moving through a kind of a funnel. So you have a section here and then a smaller section there. As the air goes through that smaller section, the pressure is going to decrease as it moves faster through that section. Well, they actually use that same principle and concept, motive flow, to move the fuel into the from the wing tanks to the collector tanks. So the fuel that flows quickly and rapidly to the engines, because their engines are going through fuel fast. Those things are burning thousands of pounds an hour. That creates a lower pressure, allowing kind of a siphon to suck some of that fuel from the wing tanks and putting into the collector tanks, and moving it to the engines from there. So another opportunity to look at, just the faster things move, the lower pressure is there. The APU fuel flows from the left collector tank utilizing DC electrical fuel pump. The DC boost pumps, I don't know how powerful they are. I've heard that if your fuel pump on your engine fails, the DC boost pump is not going to be able to provide enough fuel to the engine to continue to keep it running. The fuel pumps don't ever usually fail, but the DC pumps are kind of just there just to have something to feel good about. But there have been times where I've started an engine without having the DC boost pump on, and it starts just fine. So the second that turbine is spinning, it's going to suck some fuel in, and the fuel pumps come and they just do their thing. And the DC pumps are just kind of there to have something there, I think. Crossflow is accomplished using powered and gravity systems and is used to balance wing tank quantities. Maximum fuel balance for takeoff is 300 pounds, 800 pounds for all other times. That's the 700. So the 200 max fuel and balance for takeoff was 800 pounds. So this one was significantly reduced. Yeah, they're so for those that have their pilot's licenses and things, you've talked about slip before. So when you slip the aircraft, it's like something you do when you're landing, but pretty much you bring it on final. If you're super high and you need to get down, you press the rudder one direction and you turn the aileron the other direction to lose a bunch of altitude really fast to make it so that you can hit your point on the runway or things like that. Anyways, we don't slip a jet. You don't slip a jet. Jets don't slip. You fly them the right way. But the one time that we're allowed to press the rudder one direction, the aileron in the other direction, is to balance fuel using the gravity system. So if our crossflow is not working and we've got this massive fuel imbalance and we need to fix it quick, then we can just turn the gravity crossflow on and then slip the aircraft. So the higher wing or the higher fuel tank, so let's say the left tank has much more and the right tank is less, you lift the higher wing and then fuel just pours out into the lower tank. I've never done it, but have flown with people who have, and they said, yeah, it's pretty cool. And it moves fast too when you're doing that. And even if your wing's level and you have the gravity on, it'll still balance out just because this one's higher and this one's lower. It'll just kind of slowly make its way over. Fuel is transferred automatically from the center to wing tanks. When a wing tank fuel lever drops below 94% of capacity, fuel system computer initiates the transfer automatically. Yeah, fuel never really sits in the center tank. It only does when you're really full. And we actually have a limitation that we can't have fuel in the center tank. It has to be in the wing tanks. And if we have more than 2,000 pounds in the center tank, then we have to use a special fuel loading process because it just changes the CG and the weight and balance a little bit, not a lot, but enough that it's important for us to kind of pay attention to. So they keep it out of the center tank unless it's really full. And then on the automatic, let's see. Yep. On the automatic crossflow, so when the system detects a 200-pound imbalance, it'll automatically turn on and start to balance the two tanks. And it's not going to balance them and stop when they're the same number. It's going to overbalance and actually go up 50 pounds on the lower side. So it'll move the equivalent of 250 pounds over. As the fuel is being used, it's more than that. However, it's just that's how much they move over so that they know that the left engine was burning more for some reason. And so they compensate for that and say, okay, well, if we give them 50 extra pounds, it'll take him, twice as long to get through it to the point where we don't have to work as hard later. So that's how the fuel system works. I know, pretty awesome stuff. You really don't need to know much about the fuel system, so don't worry too much about it. This is all just great information to hopefully just supplement your understanding of everything. Okay, hydraulics. Hydraulics powers the flight controls. We talked about that. Yeah, we'll talk about this first, then we'll go into that stuff. It's equipped with 3 independent systems. Each system has 2 pumps. 3 systems, each system has 2 pumps. Main pumps A supply the normal system pressure. Pumps 1A and 2A are engine driven. 3A is an electric pump. So 1A and 2A are engine driven. They're AC motor pumps. 3A and backup pumps 1B, 2B, 3B, those 4 those are AC motor pumps. All 4 of those are AC motor pumps. We have 2 engine-driven pumps, pumps 1A and 2A, and then 3A, 1B, 2B, 3B. Those are all AC motor pumps. Backup pumps supply supplementary pressure during takeoff or landing, or when it's manually selected by the pilot. Pumps 1B, 2B, and 3B are electric. So 3A is electric pump, 1B electric, 2B electric, 3B electric, and pumps 1A and 2A are engine driven. That's I've kind of emphasized that because you need to know that. 4 pumps, 2 engine driven, 4 electric AC motor pumps. And they supplement during takeoff and landing. They turn on when we have flaps selected. So the second that flaps are greater than 0, the backup pumps turn on. Systems 1 and 2 are similar in operation except for the reservoir capacities and then what they power. So you'll see a lot of redundancy in this. Let's see. Yep. So even we look at it, right? We'll just look at the top bullet. Rudder and elevators. System 1, rudder and elevators. System 2, rudder and elevators. System 3, rudder and elevators. So that every system will power those specific controls. And then system 1 goes off of the left engine, so it only makes sense that it does the left aileron, the outboard multifunction spoiler panels, the outboard ground spoilers, and the left thrust reverser. System 2 on the right, the right aileron, the inboard multifunction spoiler panels, landing gear alternate extension, right thrust reverser, and outboard brakes. And systems 1 and 2 are cooled with a heat exchanger. And then system 3, we talked about, it only has AC motor pumps, and it powers the rudder and elevators, both ailerons now, the left and the right, the inboard ground spoiler, the landing gear, not the alternate extension, the normal extension of the landing gear, the nose wheel steering, and the inboard brakes. And so if you look at it, we talked about that when both the IDGs fail, and let's say you lose everything, hydraulic system 3 is going to power when the ADG drops. And it literally will power, we talked about all the main flight controls, the rudder and ailerons, the rudder elevators, ailerons, inbound ground spoilers, landing gear, nose wheel steering, inboard brakes. You really need all those things. So hydraulic system 3 is kind of like that emergency system that if everything fails, it's going to come through and keep it all going strong. And it has no special provision for cooling. We have a limitation on the ground that we cannot have system 3 running while remaining still for more than 20 minutes. So it's 20 minutes. It's a long time, but it has nothing that cools the fluids. The emergency electrical power ADG is provided directly to pump 3 Bravo to maintain hydraulic pressure to the flight controls during loss of AC and engine power during flight. It's a bad day. If the ADG drops, it's a bad day. Cool. Ice and rain protection. We'll get through this and we'll take another break. Thanks for hanging in there with me, guys. I know this is the most exciting thing you've ever learned, and we'll just remember that. All right. Ice and rain protection key points. Wing leading edges, slats, and engine intake nose cowls are anti-iced using engine bleed air. Okay, a lot of big words. Pretty much that just means that the compressed air that's going through the engine gets really hot. It's stolen from the engine and is used to and is rerouted to the wings, the slats, and the intake of the nose cowls for anti-ice when we turn the system on. So we have to physically flip the switches. And the 175, which is the other airplane that SkyWest has, it just turns on by itself. So they don't have to turn the switches on, but we do. So we'll turn 3 switches, and then we'll wait for a second, and then we'll watch the indication stating that, yes, it takes a second, but the leading edges, the wing anti-ice, and the cowl anti-ice is on. And we'll talk about that in the later slide, I bet. The windshield and air data probes are anti-ice using electrical power. So that's yeah, on the front of the airplane, there's a bunch of little things. There's the pitot tube, there's the static ports, there's the angle of attack indicator. There's a bunch of other different things that we have kind of on the front side. It's on both sides, so we have dual systems. But those are all heated using electric air. And we have the ice detection system. Is actually a really cool system. It just vibrates. So it's this little probe that sticks out and it just vibrates. And the frequency of the vibration remains the same unless it picks up things that stick to it. So if it's just rain, it's just going to vibrate normally and the rain's going to come off. But when things start to stick to it, the frequency of that vibration changes. And that's how it indicates to us that we're picking up ice. So it's like when people test that probe to make sure that it's working, they don't dump ice on it. Like that's kind of a weird thing to do. They just put their fingers on the probe as it's on and then wait until we hear a ding, ice, and then they let go, and that's it. So let's see, we talked about that windshield. The windshield also is electric power, and the wipers remove rain and snow from both the pilot and the co-pilot's windshield. Those are limited to a specific airspeed as well. We can't use the wipers past 220 knots. So if we get a rainstorm at cruise, we just say, well, we'll wait until we're about to land, and when we actually need to see stuff, we don't need to see things at cruise. We can be in clouds the whole time and everything's fine. But when it gets close to the ground, yeah, we need to start seeing what's going on. We have 2 ice detection systems installed, one on each side of the forward fuselage to alert pilots of impending ice conditions. These are the probes I was talking about. So they just change the frequency of that vibration and alert the pilots that there is a ice situation. The anti-ice ducting is continuously monitored for bleed air leakage. Yeah, that I'll tell you the story and then we'll take a break. So I was going into Columbia, Missouri, and we had come down through icing conditions the whole time. This was in probably early December. Coming through icing conditions the whole time. So we had our wings on, we had our cows on, we had everything, heating everything up to just keep off ice accumulation. And then we get over, we line up to the runway, we're still in the clouds, we're still in icing condition. And so the whole time coming down, we from like 18,000 feet down to the ground. I think the elevation in Columbia is like 1,200 or something. Maybe it's less. I don't remember. It's not the point. The point is that the whole time coming down, we were in ice. And then we turn on to final. And the second that we start our final approach, I have the gear down and I call for flaps 30. So the gear's down, calling for flaps 30. The only thing left is flaps 45. And we get a caution message and it says anti-ice duct. So when it's just a warning message, so it's triple ding, and then a verbal that came with it, anti-ice duct, and it shut off the anti-ice system. And we looked up, and we said, well, let's recycle it. So turn it off, turn it back on, and we just kept going. To me, it made the most sense, instead of going around and trying to figure out what the heck's going on and run through the QRH and talk to everybody that I need to. I knew that 1,000 feet and down to the ground, so like 2,000 feet lower, there weren't any clouds. It was just 1,000 feet higher, and we were at like 300 feet to get to where we poked out, and we could start to see everything. So we just continued the approach, and I felt like that was the right decision, because if I was to build time and go around, I'd be back in that stuff. And if our anti-ice system wasn't working, then we would just accumulate a bunch of ice that would change the shape of the wing, that would increase the amount of weight that we'd have, and it would severely affect the ability. Sorry, I don't know why it went off. All right. Anyways, and so we continued down, got on the ground, and then taxied over to the gate. Everything was fine. We got down. The system ended up just having a fault. And so we wrote the airplane up. Maintenance came out, looked at it, said, "Yep, it's fine. Go back to Chicago." And so we did. But we didn't hear anything about it other than just kind of looking back at it and just you kind of debrief yourself. Hey, what should I have done? What could I have done? Was this the right choice? Kind of going through things like that. But what happened was the anti-ice system had detected a leak, and it informed us of the leak. And the reason why that's important is because this air that's getting ducted through to anti-ice the wings and the cowls, it's super hot, and that it could cause damage to the wings, to the systems. So the second that it detects a leak, it's going to notify us and then shut everything off. That way we don't damage the system even more than it already is. So, okay, well, let me make sure that that's it for the ice and rain protection. So we'll take a break real quick. Okay, we'll go through that. I think it's only one more slide. So cockpit windshields and windows are constructed of 3 laminated glass panels separated by 2 vinyl layers. The inner surface of the outer glass panel has a conductive coating that is electrically energized for heating. Pretty much just says that that's how it gets heated, and it keeps the ice off, and it does a good job. I haven't had any issues getting ice on the windshield. On the first place that we'll notice it is actually on the windshield wipers. We'll look, and there's the things that poke out that are small are the first things that show that we're getting ice. So just the little probes and things like that. But okay, cool. That's ice and rain protection. Let's take a break. Be back at 45 past the hour. Okay, welcome back. Thanks for staying invested. I know this is the most exciting thing you've ever learned. So, got a few more slides, and then we'll run into the QRH, run through a procedure, and we'll talk about kind of what we see in the flight deck with what happens if we do have a failure, and the order of things that we're supposed to do things in. Like I told you, I messed up the order when we had the IDG failure from Chicago to South Bend. But yeah, we'll go look in. Maybe if you want to look into that one too, we can look into it, because that one had like 4 different messages come up all at once. So we can go through kind of all those that came up and how to fix them all. But yeah, so we'll get into the ICAS now. This is the Engine Indication Crew Alert System. Indicating and recording. This is pretty much just the computer that tells us what the engines are doing and how the bleed air is being ducted around and things like that. Okay, so the indicating and recording system consists of components that display or record critical aircraft information and system operation. The function of the ICAS is to display the engine instruments, visual and oral crew alert messages, and real-time interpretation of aircraft system operation. Does it talk about the 4? Oh yeah, color logic. We'll go through a little bit of this, and then I'll kind of talk a little bit about it. The engine indication and crew alerting system provides automatic system monitoring, integration of system monitoring, color logic for presentation of minimum maximum limits, and our oral alert warning messages. Like when I told you, it said anti-ice duct. Like that was the words that came out of this thing. It's crazy. Also, like if we have the passenger door open while an engine is running, the thing will go off. It'll go door, and I'll just say that over and over and over and over again. Indicating and recording key points. Information is provided in the 2 cathode ray tubes located on the center instrument panel. Master warning and caution lights located on the glare shield. What? Okay, here we go. This is what I really wanted to look at just initially. So when we talk about the message importances, the most important message that we need to know about now is associated with so 3 things come with it, and sometimes 4. So a triple ding goes ding, 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 and then the message pops up. So the triple ding, the message, and then on the glare shield there's a switch light that we push to reset the system. Anyways, there's a switch light that pops on. It pops on red for warnings. Caution, same thing, except for 1 ding, and the caution button turns on and it's amber. The advisory messages, this is just advising you of an aircraft state. So some messages that we see a lot, fuel pumps are on. The thrust reversers are armed. The wing and cowl anti-ice is on, things like that. And then status messages are like least important things. For example, the 2 status messages we always see are that the no smoking sign is turned on and the seatbelt sign is turned on. Things that really have nothing to do with the engine, but this is where they are indicated and recorded and reported to us. So the crew alerting system provides visual and oral alerts when the data concentrator units detect a malfunction. And then this is another important one. The CAS prioritizes messages by order of occurrence and order of importance. So all the red messages, they're going to stack up by the most recently occurred one. So let's say you have passenger door opens, and then you have left engine shuts down, the oil pressure is bad, and then the right engine. So it's just going to continue to stack on the order of occurrence. So the door opened first, so it's going to be at the bottom, and then all the other stuff stack on top of it. And then underneath that, that's where all the caution messages will pull up. And then that's on ED1 and ICAST display 1. We have 2 display screens on the front here. ICAST display 1 has the warning and the caution, and then ICAST display 2 has the advisory and the status, the less important. They're all important, but the less important ones. Messages show up there. And we talked about master warning and caution lights located on the glare shield. It's just a kind of a strip right underneath the windscreen that it has where we turn on our autopilot and stuff like that. It also has where we can discharge halon bottles and things like that. So I should, I should have pictures of all this stuff and be able to kind of point things out to you, but it's not a lot of the stuff that you need to know. I'm trying to emphasize the points that you do need to know, and I don't think there's anything with this one. So just know that we got a bunch of screens that tell us a bunch of information, and they prioritize it by importance. So the ICAST primary page. Let's see if I can pull one of these up. ED1 survey. So. That is most definitely 2. There it is. Oh, well, I can't find a way to make it super visible here. So anyways, we won't do it. I'll work on this next time and have a better presenting method next time. So the primary page shows the N1 speed. The N1 is the fan. When you look into a jet engine, it's the little turbine fan that you can see right there. That's the N1. So the N1 speed, and it's reported in percentage of max RPM. So it's reported if you're at 50% N1, that means 100% is the max RPM that'll go, 50% half that. ITT, internal turbine temperature. And 2 speed. So these are the turbines that are in the engine core. And it's also recorded in the same way, percent of max RPM. It's just the percentage of the max. The fuel flow, how many pounds per hour? This we look at pounds per hour. Oil temperature, oil pressure gauges, and N1 fan vibration gauges. The N1 fan vibration, it's not always 1-to-1, but when it's vibrating, there's different things that it could equate to. If it's picking up a lot of ice, then it'll start to vibrate, and you'll start to see that kind of get a little more. They also associate just the engine aging and getting older with higher vibrations, which just means that it's probably going to, not probably, it might. Jet engines are very reliable, but if the vibration gets too bad, it's going to fail, and it's not going to be a great day for whoever has to deal with it. So that's on the primary page. The secondary page is called the status page. So ED1's primary status page. This shows the crew alert system advisory, which are the green, and the status, which are the white messages. And it also shows the APU status, 2 gauges. It shows the exhaust gas temperature as well as the RPM of the APU. Kind of the same situation with the N1 and N2, but the APU, it always runs at 100%. So it should always say 100%. Sometimes it's higher, sometimes it's a little lower, but it usually just says 100%. We input the flight number. It's in the top right section. The trim settings, and this has all 3. So it's got the elevator trim, and that's displayed as a number. And depending on what phase of flight you're in, it's going to depend on the number that you're using. If you're in a takeoff phase, there's a section of it that has to be green, so it's like green for takeoff. It's from like 5.0 to like 8.0 or something like that. So anything in that range, you're good to take off with. And then when you're at cruise, you're at a really low setting. And when you're upon approach to landing, a lot of times you're at a really high setting. Sometimes I've seen people land the airplane and I look down and as a first officer, they reset the trim after every single landing. They set it to 7. So there have been times where I look at it and it's at like 12. And I'm like, dude, were you having to push down just to descend? And they're like, yeah, but that's how I like to do it. I was like, okay, well, you do what you like, I guess. Everyone's different. So that's trim setting, crew oxygen pressure, cabin pressure and temperature, brake temperature. That's something that we pay attention to quite a bit, especially when it's hot in the summer. We can't take off if the brakes are too hot, just due to the fact that we might have to abort, and we don't want to do so with really hot brakes to the point where they're about to catch fire. So, brake temperature is a big one that we worry about, and that's the status page. And then I kind of mentioned this as going along with the multifunctional display. It's not the multifunctional display. It's the synoptic pages. And this will show up on ICAST display 2, which is where the status and the advisory messages are. And it's all these different pages. So the ECS, the Environment Control System, the hydraulic pages showing the temperature of the hydraulic fuel, the hydraulic oil, the quantity of the hydraulic oil, and the pressure in the lines, and the systems that those specific hydraulic systems are powering, like the elevator, the rudder, the left aileron, the right aileron, both ailerons, and things like that. AC electrical, DC electrical, fuel, flight controls, anti-ice, and doors. The AC and DC, this to get to each of these pages, you just have to click the electric button twice. There's not, like for all these other ones, there's a specific button that I can click and go straight to the fuel page. But for the AC and DC, it's just the electrical button, and you have to hit it twice to go see the different pages. Not anything you need to know. This is a cool kind of feature. So it's inhibit logic. ICAST message inhibit logic. Minimizes spurious or distracting warning or caution messages during the initial takeoff, final takeoff, and landing phases of flight. Pretty much, it doesn't tell you messages that really don't matter during important, critical phases of flight. And then once you're on the ground or once you're in the air and finally things start to have calmed down, then boom, you'll get all those messages and they'll pop up and go, oh crap, now I got a lot of stuff to do. So yeah, that's a really cool feature about it. The one message that I've kind of talked to you about, the EFIS Comp Mon, which just tells you the headings off. We'll get that sometimes on our takeoff roll. And on the takeoff roll, it's not like a very stressful time until you get dings and warnings and cautions and messages, but you're always on edge because we're hauling down the runway. And once we hit our decision speed on whether or not to take off or to abort if we have a problem, you have to make a decision super fast. So we'll be just chilling, just doing our thing, normal takeoff, and next thing you know, bing, and I look over, I'm like, freak, what's that? Oh, EFIS, continue. That's what. So I get my heart rate and my blood pressure all increased for an EFIS Comp Mon, and I just, well, it's just EFIS. We'll keep going. We'll fix it later, and it ends up, it's just due to the magnetic fields around the aircraft on the ground. So nothing crazy, but I wish that one was inhibited more. For some reason, it gets through all the inhibit stuff. So FDR records the last 25 hours of flight data using solid state memory. And the MDC maintenance diagnostic computer records engine and system parameters. Data can be downloaded for system diagnosis and fault identification. This one's really cool. We're not, as pilots, we're not like trained on how to use this, but we also just can if we know what we're doing. But it's a switch that we turn on that pulls up all of the current faults and the fault history and tells us what happened and why it happened. So, for example, a first officer and I were in Tucson, Arizona. And in order to start an engine for the 700, you have to have 20% N2 rotation and less than 120 degrees internal turbine temperature. So over 20 rotation, less than 120 degrees, and then we'll initiate the fuel. However, if the thrust lever is brought into the idle position before the ITT is reduced below 120 degrees, then it's going to go into an automatic abort start, automatic. And so then we just do our check. Goes, okay, we shut the thrust lever off and shut the engine off. And then we'll run through all the checklists that we need to go through. And that just happens just because at that one specifically, the first officer introduced fuel before the temperature was cold enough for the engine to want to start. But anyways, I don't watch every single engine start. Like, the first officer should be knowing what they're doing, and they should be just paying attention to the point where I don't need to watch everything. I don't watch everything that they do because they've done it hundreds and hundreds of times. And so anyways, I look over and I go, okay, well, why didn't it start? And he goes, I have no idea. And I was like, well, you probably initiated fuel too soon. We'll say that's the reason. And then we ran through all the checklists. I said, we didn't exceed any limitations. We're good to continue. Let's try again. Start the engine. Starts it. Everything happened normally. Started fine. No issues. We get to our destination, which was LA at this time. And we get to the gate, and he goes, do you want to write up the startup board? Because it was a mechanical irregularity. I was like, it wasn't a mechanical irregularity. You introduced fuel before the temperature was ready for it. Well, I don't know. I didn't remember the fuel number or the temperature number. I said, okay, well, let's look at the maintenance diagnostic computer. I flipped it on, pulled up the fault history, and sure enough, it said fuel was introduced before the ITT was lower than 120 degrees Celsius. I was like, there you go. The system said that you introduced fuel too soon. It aborted the start. We tried again. Everything worked normally. I'm not writing it up. Maintenance doesn't need to come take a look at it because the system performed normally. And that's just, it's a really cool piece of it's kind of like your check engine light in a car. But this one's like way more cool because it tells you why things are the way that they are. It'll tell you specific sensors that have failed that need replacing, and things like that. So the MDC is super cool. And the data can be downloaded for system diagnosis and fault identification. So yeah, it kind of helped. It helped solve an argument for sure. My first I was like, no, we got to write this up. And I'm like, no, you didn't start the engine right. I'm not having maintenance come look at it because of your mistake. And well, that was enough said. Landing gear. So we have the standard retractable tricycle configuration. Hydraulic system 3 powers the landing gear and nose wheel steering, and then 2 and 3 operate the brakes. The system 2 is the one that operates the alternate extension. So system 3 power doesn't work and isn't able to drop the gear, then system 2 will drop it using the alternate method of lowering the gear. And then also manual gear extension is available. That there's a lever for us to pull that it actually tells us to pull it while standing. So it's one of those levers that you will get out of our seat, stand up in the little area that we have, and reach down. And I guess this thing comes out like 1.5 feet to 2 feet, and then that's when the gears swing down. So it's a pretty big one. And we talked about this a little bit with the overheat detection system, but main landing gear overheat detection, and it's just those loops. So the second that it can sense a difference in resistance for the electricity going through the loops, if it's easier, then it'll detect an overheat situation. The nose wheel steering is hydraulically actuated and accomplished using steering tiller or movements of the rudder pedals. The tiller's on the captain's side, it's on the left side, sits underneath, like, yeah, it's kind of like forward on the left side, so my left hand's on it. And it can turn the nose wheel up to 90 degrees. I don't know the exact number, but I believe that if you press the rudder pedal all the way down, it will only turn the nose gear like 10 degrees or something like that. So you have much more ability and capability to turn using the tiller than you can with just the rudder. So accomplished using steering tiller or movement of rudder pedals. What is interesting is the nose wheel steering can actually be, it's a deferrable item. And I didn't really think too much about it because, you know, when I was doing GA thing, I flew a Diamond DA40 when I was doing my training. And that one doesn't have a tiller and it doesn't have any sort of nose wheel capability. It's just a free cast-string nose wheel. How you steer is by just tapping the brakes. So you use the thrust to go forward, and then if you need to turn right, you touch the right brake. If you turn left, you touch the left brake, and then that'll turn the aircraft. I thought that is just, it's easy. So just tap the brake. And when I started flying the Seminole, that was my twin that I flew, the Piper Seminole. Then we kind of introduced the differential thrust. So, okay, you want to turn right? Well, keep the thrust on the left, on the right engine down, and increase the thrust on just the left end of the engine, and see how that turns you. And that was pretty substantial as well. Those are wing-mounted engines, and so the just the arm, the capability for the force out on the wing to turn you to the right was much higher than I thought it would have been with the CRJ, because our engines are mounted on the tail with the arm from the center of gravity only being like probably like 4 or 5 feet. Nothing real crazy when you got like a super 69'8" wingspan. Anyways, we when I was in South Bend, we had an opportunity where we push back, and we don't turn the nose wheel steering on until both the engines are started and we've checked our flight controls and we are ready to taxi. So I turn the nose wheel steering on, and bing, nose wheel steering in op. Turn it off, turn it back on, bing, nose wheel steering in op. So it wasn't working. And so instead of taking South Bend is a maintenance place for us. And so I called maintenance up. I said, hey, this is having problems. I see it in the history. It's been written up before. I'd like to return to the gate, have you guys come fix it here. And so at the time, I only had a single engine, just because in South Bend, it's hard to kind of guess the flow time into Chicago, just being how close of a flight it is. They have to have windows for our aircraft to take off and get into the flow of the arrival traffic. And if they don't have windows, sometimes I've sat on the ground in South Bend for over an hour just for a 22-minute flight, waiting on just a window for us to take off and to come into Chicago. Anyway, so that's why I was only on one engine and didn't really think about it. But once the nose wheel steering problem, we decided to return to gate. We got everybody in place, and all I had was one engine. And I increased the thrust in that one engine, thinking that it wasn't going to be that big of a difference. And next thing you know, I had to slam on the brakes because I was not able to control how hard of a turn that it made. And so I was like, well, start the other engine, and we did. And then to get back to where we needed to be, I just used that engine to correct for it, and then everything was idle and just inched forward. It was painful. I'm sure it was painful for everybody watching. It was horrible for me. So, but yeah, nose wheel steering is huge. It can be deferred, but it's a pain in a jet to try to taxi around without a nose wheel steering. And maybe it's just because I haven't done it in a really long time, but it was hard. And yeah, so nose wheel steering is awesome. Dual channel inboard and outboard anti-skid systems. So this is with the inboard and outboard brakes, anti-skid, so it just doesn't lock up the brakes. It's the same as your car. So if you're landing or if you're driving in snow and you slam on your brakes, the system isn't going to just let your brakes just take over and then just skid forward. It'll reduce the pressure of the brake pad on the rotor, and the wheel will continue to spin as it slows down. Same thing with an airplane. When we land, if we slam on the brakes too hard, it's not going to lock up our wheels and pop our tires. It'll give us the max amount of braking that we can get without doing that. BTMS, brake temperature monitoring system, monitors the temperature of each brake, and it's displayed as color-coded numerical reading on the ICAS status page. Does it say anything more about that? Nope. So it's colored. Green is 0 to 6. Is that a 5 or 6? I think it's 5. 0 to 5. Green is 0 to 5. White is 6 to 10, and red is 11 to 15. Red is like, I've never seen red. I've seen white. I've seen a 6. I've never seen more than that. But I've never seen red. So red's bad. We had a company-wide email because of this. But while crew was in the CRJ, was up at 32,000 feet or something, cruising along, they got a landing gear or a brake temperature monitor system. They got a red indication on one of their brakes at cruise. They hadn't any issues, but all of a sudden at cruise, they got this red indication saying, yo, this brake is hot. And I forget the associated message with it, but I think it was a brake overheat caution message that popped up as well. Anyways, so they ran through the QRH, and without really thinking about what they were doing, they dropped the gear at 32,000 feet because that's what the QRH told them to do. And so you had a 0, a 12, let's say, so a red gear overheat situation, and then another 0. So it was 3 cold brakes and then 1 hot one. And they dropped the gear at altitude and quickly realized that they were not able to maintain altitude just because of the amount of thrust that you have at altitude is a lot less, and you're not able to maintain it if you drop that much drag out all of a sudden in the middle of that 32,000 feet. I think they ended up having to declare an emergency and immediately started descending down to 20,000 or something like that, and continue running the checklist, and everything turned out to be fine. Well, the message that the company came out to us and they said was, this was a erratic readout, just because one of the, three of them were green and zeros, and really all 4 of them were, but unfortunately, and for this case and for them, they had a readout that was wrong, and just pretty much warned us. They said, just use your brain a little bit. When we're dropping gear at 30,000 feet, you're not going to be able to maintain altitude. So you'll need to figure out, if you truly think that it's not an erratic readout, then descend first, get everything in place, and then slow down so you're not exceeding any aircraft limitations, and then swing to gear and continue with the QRH procedure. But the brake temperature monitoring system is a good system, but sometimes it has its faults, and especially at 32,000 feet, if all of a sudden you're seeing a 12 and everything else is 0, then yeah, it's definitely not something you should trust. The tail skid plate is installed on the aft fuselage and prevents the tail cone from making contact in the event of a high rotation pitch angle during takeoff. We have had some, it's always on takeoff that we've had some problems, but I don't know why Atlanta is the way that it is, but and LA is this way too, but they land on the outer, there's 4 runways. In Atlanta, there's 5, but we'll just pretend that there's 4. and they land on the outer runways and they take off on the inner ones, which makes sense. Taxi the inner one, take off, land on the outer one, and then taxi around the inner one to get to the gate. And like I said, same thing in LA. And anyways, on runway 26 left, it starts flat, and then right as you're about to hit rotation speed, or it starts flat and then it starts to go down, and then right as you're about to hit rotation speed, the concrete starts to come back up. And so just how everything is and how people look at it and the rotation, they actually over rotate and sometimes will hit the tail on the concrete while they're rotating because of just the weird way that the runway is. And yeah, we've had a few issues with that, and it's only in Atlanta that we have those issues. So but yeah, tail skid into play is it prevents the tail cone from making contact, and it also just alerts the crew, hey, we've had a tail strike, and so we need to do a tail strike inspection, make sure that nothing's broken. Not all 700s have this. I've flown a bunch of 700s that do not have it, but most do. Most do. Lights. Lighting systems include external lighting, flight deck lighting, passenger compartment lighting, service compartment lighting, and emergency lighting. Bunch of lights. For aircraft visibility, you got nav lights, and those are left green, right red, and so on the left wing there's a green light, on the right wing there's a red light, on the back you can see a white light. Anti-collision strobe lights, those are just flashing white lights. Fun fact, Boeing flashes one time. So if you see a 737 or a 320 in the air, you can tell which one it is because the anti-collision strobes will strobe one time on a Boeing, and on Airbus they'll strobe 2 times. So that's a fun fact for you. Rotating beacons, the red beacons that go around. Logo lights, which just illuminate the tail, and the wing inspection lights, which help you look at the wing if we need to inspect the wing before we take off due to the snow accumulation or something like that. Then we'll turn the wing inspection lights on, and it just illuminates the whole upper surface of the wing. Lighting for external illumination, we got taxi/recognition lights, nose landing lights, wing inspection lights, and emergency lighting. This is for the passengers mostly. Wall and floor level exit signs, cabin and floor level emergency floodlights, and floor track photoluminescent tape. That's it with lights. Nothing crazy there. You don't need to know anything about them other than that an airplane has lights. Navigation key points. We got dual VHF, DME, LOC, navigation systems, dual ADF nav, dual marker beacon, dual transponder. This one is probably the only one that really matters. Everything else is just, yeah, we have these systems that we use to navigate. When you get into approach plates and things like that, you'll learn a little bit more about localizers and about GPS and about VORs and things like that. But for now, just know that our aircraft the 700 can detect pretty much anything and can shoot any approach and things like that. Dual marker beacon transponders. We always operate with the transponder pointing to the pilot flying. I've always thought that it's just because if we ever get in an accident and everything happens, and nobody survives, they'll go on the flight deck and look and see who's flying. And the only thing that can point to who was flying immediately is that switch, because that's the only one that will stay pointed in one direction or the other. So the switch position, that's kind of the only reason why I think we do it that way, just so, immediately they can figure out who messed up. That's the captain's problem. But go ahead, Brett.
With the dual ADF, do you guys fly a lot of NDB approaches? Are there very many of those still working?
No, I haven't flown one yet.
Okay. Just curious.
Yeah, no, the majority of the ones that we fly it's like, I think probably 75% ILS, 15% RNAV or GPS, and then the other 5% or 10% is or VOR approaches. But I
That
mean,
makes sense.
most of the places we go to have, if they have RNAV, like we fly the RNAV. Keep it simple, you know. If there's an ILS, fly the ILS. Keep it simple. Don't complicate things. Some people
Yeah,
like to do. Go ahead. Sorry.
So the only NDB I even know about that still works is just west of Tucson.
Just west of Tucson or at
Yeah.
Tucson?
I think it's west of Tucson by the Ryan Airport.
Huh. Okay.
Anyway, that's the one I even know about.
Well, I'll take a look next time. I'll look around and see if I can see any of the approach plates that the airports I go into within the next month or so. And if I see anything, I'll reach out. But yeah, as far as I know, I haven't flown an NDB approach ever.
Okay.
Some more navigation systems: EgyptWiz, engine or enhanced ground proximity warning system, weather radar, TCAS, and GPS. So the other thing I want to mention with TCAS, for those that are familiar with it, you might know what TA and RA are, but that's traffic advisory and resolution advisory. So if you have two aircraft, let's start with one. Let's say we have the CRJ 700 and it's having a situation with a Cessna 150. Okay, so you're coming together. The Cessna 150 has no sort of TCAS on it. It can probably has a fish finder, probably can say, oh yeah, there's traffic over there. But that's probably the extent of its TCAS. And so the CRJ that has the TCAS system will look at it and say traffic alert, you know, it's down, and it'll say -100, and it'll show its location and reference to you. And so then you can look, okay, he's over there and he's down 100 feet. And so you look down, okay, there he is, we found him. Let's say that there's a situation where you have two CRJs and they have a situation where they come close in contact with each other. It'll first start out with a TA, a traffic advisory, and then it'll turn into an RA, a resolution advisory. And this will tell both aircraft different things to do. So if they're coming in head on each other, they're going to say, okay, this guy you climb, this guy you descend, and this guy you turn, and both you guys turn right. So it'll have them coming at each other, and then boom, up and over, and that's how they'll resolve this situation of a close contact with another aircraft. But that's only if both aircraft involved in the alert have a TCAS system on board. And then GPS, that's the new stuff. GPS is huge right now. Go ahead.
On the RA system, is that I mean, if you have that, are you required to do as instructed by it?
Under certain circumstances, yes. Not all circumstances, though. If you don't have a traffic in sight, you should comply. You should comply. And
Yeah.
ATC is going to respect the fact that you complied. All you have to do is say air traffic control, because you're now deviating from what they've told you to do. You just say, hey, Center SkyWest 1025, responding to an RA. And then once you respond, you get out of the situation and you say, okay, SkyWest 1025, we're ready to navigate as you wish or whatever like that. But they'll always respect the fact that you're keeping yourself safe over. And the same thing with like the enhanced ground proximity warning system. I hate center. You almost flew us into a mountain. We're climbing right now. You know what I mean?
Yeah.
So yeah. So it's in cases like that. Yes, you should follow it. But like for example, in San Francisco, those runways are like 100 feet apart. Maybe they're more than that, but still, you get the idea. And the approach for the left runway, it's a straight in approach. And then for the right one runway, it's kind of an offset angle up to a specific point. And then you wings level, and now you're both flying next to each other for the last, I don't know, probably 2-3 miles, maybe more. And in those situations, I've actually had the RA going off the entire approach.
Oh,
The
man.
reason that we don't have to comply with it is because I can look over and I say, nah, I can see him and he's over there and he's doing what he's supposed to do. We're going to keep doing what we're supposed to do and everything's going to be fine. So
Yeah.
in only situations where you can literally see them and say, okay, well, they're doing what they're supposed to be doing. I'm doing what I'm supposed to be doing. We're going to continue.
Okay. Yeah, I asked because I can't remember the situation, but I seem to remember there was an accident sometime in the past where there was a situation where one of the pilots did actually the opposite of what the RA was telling them to do, and I think they collided or it was a near collision. I can't remember the detail, but I just remember something like that happened. So I was wondering if the FAA had put anything to enforce that or anything.
Yeah, no, nothing that I'm aware of. Yeah, if you do exactly what it tells you not to do, there's going to be some problems. So you either comply with what it's telling you to do or keep doing what ATC has asked you to do, which is either continue the approach or follow the RA and get out of there. Go ahead, Christopher.
When you guys are in the terminal environment, your checklists don't have you go to TA only? Or do you
No.
leave it in TARA all the time?
Yeah, I never change it. It stays in TARA the entire
I don't
time.
know why our procedures all, military flying, we would always go TA only in the terminal environment. I think exactly for the reason he was just, like you said, it gets really twitchy in certain, flying in SoCal or up there around San Francisco, it gets twitchy.
Right. Yeah, that's interesting. I didn't know that. For us, they just say have it always on, and then if you can look at it and say they're doing what they're supposed to be doing, I'm going to continue doing what I'm supposed to be doing, and everything's going to be fine. Then you're totally okay to not have to follow the RA. But yeah, interesting. I didn't know that you guys. What'd you fly in the military?
Flew C-130s primarily, and
Okay.
I flew UC-12 Whiskies, which is King Air 350.
Cool.
Favorite
There you
job
go.
ever.
You trying to get into an airline job or just is dispatching?
Actually, I currently have a dispatching job. It's just kind of a hokey one. I work for Kuwait Air Force. I dispatch their flights worldwide as a remote job. I'm looking to actually head back out to Kuwait. I was a pilot instructor out there previously. Then I took the dispatch job as a remote job to kind of be home more. Anyway, they want me to come back out. Beautiful. If you want me to do that, then I want to be a real dispatcher. So here we go.
A real dispatcher. I hate it when people come up to me and say, "Oh, you're finally a real pilot because you're a captain." I'm like, "Nah, dude, I've been a real pilot for 4 years. Back off." Oh, well, now you get to fly the real plane. No, the small planes. No, it's little, large. Get it right. Little, large. And I've been a pilot for 4 years. Those are my two things I will have a little bit of fire and passion about. So if I fly a little large airplane, and I've been a pilot for a long time. So,
But TCAS has saved me from, I'd say, at least 3 either near mid-airs or mid-airs. I would say you get the RA, you follow it.
Yeah, I agree with that. There was one situation where we got an RA, and I heavily regret not following it, but I wasn't flying, and the captain said, "No, we're not following it." He was the one that was flying. I was a first officer at the time, but it was on downwind, And pretty much I knew exactly what was happening because they told the aircraft that was behind us to slow down. So they were eating up ground on us super quickly. And they turned us base to start setting up for a final approach into Salt Lake. And this guy was still just hauling. So as we turn base, he's closing the gap quicker and quicker and quicker. And as we're turning base, obviously we are not getting away from him. We're just staying kind of a slow turn, making our way over towards final. And it gave us an RA, and we were IMC. Captain's like, no, he's on down when we're going to continue. So we continued, but the IMC, you can't see anything. And so it's really hard to justify not complying with that specific RA because we couldn't visually see that he was doing what he was supposed to be doing. We could just hear that center was trying to manage a situation that could have gotten a lot worse. So I agree with you. I haven't had any sort of close air collisions or anything like that, thankfully. And I hope to never have one. But yeah, after that day, I kind of have been respecting the TARA, the RAs especially, a lot more because I'm like, dude, you just never know. Last thing you want to do is to be in a situation where you don't get to go home after a trip's over, and so yeah, it's everything you can do to maintain as much vigilance and safety as possible. Absolutely. So. Yeah, thanks. Good luck with dispatching and becoming a real dispatcher. That's I'm happy for you. Hopefully it all works out.
I appreciate it.
Yeah. Okay, how much more? Okay, we got 2 more of these. We'll take our last break and then we'll come on back. So navigation key points, we'll still be on with this. Each navigation radio is capable of receiving a VOR DME and 2 additional DME channels. This just helps. Sometimes there's a localizer frequency you have to tune to, but also you have to do a DME hold. There's a different frequency that you need the distance. So DME, I forget the exact, oh no, I don't know. It's distance measuring equipment or something along those lines. So sometimes you'll be tracking a localizer, but the DME that you need to be tracking is a different frequency. And so you can do what we call DME hold, where you plug the DME frequency in first, you click hold, and then you swap the frequency to the localizer frequency. And now it displays 2 things. It displays the localizer, and then it also displays the DME of the beacon or the VOR or whatever you need to be tracking there. So 2 radio tuning units, and the TCAS provides a resolution advisory for traffic considered a threat, and that's within 25 seconds of collision. So if you can run into somebody within 25 seconds, then it's going to tell you to do something different. EgyptWiz calls out altitude callouts, excessive bank angle, excessive descent rate, excessive terrain closure rate, unsafe terrain clearance, altitude loss after takeoff, and wind shear detection and alerting. Yeah, EgyptWiz is awesome. I've had a few terrain EgyptWiz. Notably in Cedar City, they actually, when you land north, so coming from Salt Lake, you have to kind of go all the way around and then come north. There's a tower that they built right on final, and it's been given a whole bunch of EgyptWiz callouts recently. So that one's the only one I think I've ever had. And yeah, I mean, it's a good thing to have, though. It's nice. I've been grateful and thankful that I haven't had any sort of issues or any sort of call outs with this yet. But obviously we're trained to respond to whatever it tells us to do. You do it, and unless you can guarantee, oh, yep, that's the tower that it's telling me about. I see it. I'm going to avoid it. It's off my right. I'm going to stay to the left and go land. So that's another thing that's the same way with the RA. You can not worry about it if you can say, okay, that mountain's not moving and I'm not going to hit it. So we're good. All right. Let's take another break. We'll do 50 after 50, and then we got 40 more minutes, and I'll let you guys go. So when we get back, we'll finish this really quickly, and then we'll do the QRH things and then call it a night. So be back 15 minutes. Okay, welcome back. Final push through this, and then we'll be on to looking at QRHs and go from there. So we got a little bit more slides than I was hoping for, and we'll just get through them as quickly as we can. That way we can get to QRH, spend probably 5-10 minutes on that, and then let you go for the night. So yeah, here we go. Oxygen and emergency equipment. Oxygen is supplied to the flight crew, flight attendants, passengers during emergency. Those will deploy at 14,500 feet. When the cabin pressure, cabin altitude is 14,500 feet, those will drop for the passengers. The flight deck is supplied by gaseous oxygen bottle. Flight attendant and passenger drop-down oxygen masks are supplied by chemical oxygen generators. So they never run out of oxygen. They'll just keep generating them. Does that mean that if you're at 30,000, you have a rapid decompression or depressurization, anything like that? And does that mean that we'll be able to get down to a spot before people start passing out? No, but it won't. Nobody will die because it'll probably just pass out for a minute just due to oxygen deprivation. And then when we get down to low enough altitude, you'll wake back up and everything will be okay. Therapeutic oxygen is available from portable oxygen cylinders. Crew masks are full face, quick donning, and equipped with a microphone, and chemical generators provide oxygen for 13 minutes. If you don't take it seriously and take longer than 13 minutes to get down to a safe altitude, then that's on you. So it takes rapid descent, 5,000 feet per minute from 37,000 feet is not going to take that long. Much shorter. So probably like 5 minutes. Okay, passenger masks deploy at a cabin altitude above 14,000 feet. I guess 14,000. Passenger masks can be deployed manually from the cockpit. We have a button. It's a guarded switch. We just lift it up, press it, and they drop. A PBE, protective breathing equipment units, are installed in the flight deck and passenger cabin to provide oxygen and smoke protection for flight crew members. Yeah, those are great. Okay, emergency equipment, fire axe, fire extinguisher, overhead hatch escape rope. This is on the flight deck. We do have a fire axe in the flight deck. Life vest, flashlights, over wing emergency exit escape ropes, and a megaphone. Pneumatics. You don't need to know much about the emergency equipment or the oxygen systems. So pneumatics. During most phases of flight, the engines supply bleed air for the system operations, and the pneumatic system is managed automatically. Pneumatically, we can use one engine to start the other engine, and we can use the bleed air from the engine to do the cow and wing anti-ice, as well as provide air conditioning. So it literally does it all. The 200 sometimes will need to start the APU in flight to help with load, but not the 700. The 700 APU doesn't come up until we hit the ground. Pneumatic system receives pressurized air from either the 6th or the 10th stage, the APU, or from an external ground source. The common air manifold distributes the bleed air. It's a fully automated with manual control available for non-normal operations. Yeah, this is a difference. The 200 was fully manual. You had to select what valve you wanted open and how you wanted it to work every single time. It's pretty frustrating. But with the 700, it's fully automated. You just, when the APU turns on, it takes the bleed air. If you turn the anti-ice on, then everything switches to the engines. And then if you turn the anti-ice back off, it's hard to get it back to the APU automatically. So you end up doing that kind of thing manually, and you just select, there's 3 knobs. One is where you want the bleed source. So from both engines, left engine, right engine, or APU. So you turn it to the APU. The ISOL valve, you'd want that open so that it doesn't isolate the 2 systems from each other. It makes it one system. And then you would turn it from auto to manual. It would copy what you have in that box, those two other switches. And then once it goes from there, you turn it from manual back to auto and it will stay on the APU. And then you configure the switches that they're supposed to be with ISO closed and the other knob, the source selector on the both engines. So to minimize damage from bleed air leak, the pneumatic ducts are continuously monitored by bleed air leak detection system. We talked a little bit about that in the wing anti-ice, but the hot air can do a lot of damage. So it's continuously monitored to make sure that the damage that is done is not detrimental to the safe operation of that specific flight. The sixth stage of the engine compressor supplies air to operate pneumatically powered systems. When system demand exceeds the capacity of the sixth stage, high pressure valves automatically open to supply higher pressure 10th stage bleed air to the manifold. So it uses both 6th and 10th stage. 200 uses 10th and 14th stage bleed air. So it's kind of annoying having to know the differences there. Power plant, we talked about the engines. 2GE CF34 8 Charlie 1 or 8 Charlie 5 Bravo 1 high bypass turbofans. So high bypass just means that the amount of air that goes around the engine core is greater than the air that goes through the engine core. And high bypass engines are better for operation at lower altitudes. That fan N1, that N1 fan will be able to generate much more force at lower altitudes using that bypass air. And then at higher altitudes is when the core, the engine core, the air that goes through the engine, that's where that will shine, and that's where the internal core will provide most of the thrust at higher altitudes. Normal takeoff thrust rating 12,670 pounds. One engine operation with thrust with APR, which is automatic power reserve, is 13,790. So just if you lose an engine, the engine recognizes, hey, we lost one, we need to work a little harder. And so it increases to that 13,790 pounds. They're flat rated to ISO plus 15 at sea level. And each power plant is controlled by FADEC. We talked about FADEC. And the engine has two independent major assemblies, N1 and N2. Those are the fans. So the N1 is that forward fan that you see, all those blades. And then N2 is the stuff you don't see. It's inside the engine. And it's where we get the bleed air and where all the air really compresses to compress and then burn and then be exhaust. N1 consists of a fan rotor that is driven through a shaft by a 4-stage low-pressure turbine. N2 section is comprised of a 10-stage axial flow compressor, combustor, accessory gearbox, and a 2-stage high-pressure turbine. Pretty much just fancy words for saying there's a bunch of stuff that happens to an engine. If you want to get into it, you can study more about it. But for the purposes of this class, you need to know N1 and N2 are two different sections. And the N1 is the stuff you see. The N2 is the stuff that you don't. The N2 pressurizes the air. And the N1 is just, it's better for, it provides more thrust, lower altitude when you're doing takeoff and land operations. Usually it's a high bypass, which just means most of the air does not go through the engine core, it goes around it. Engine airflow passes through the single stage fan and then is divided into two airflow paths, bypass air and core air. We're kind of talking about that right now. The bypass air is accelerated by the N1 fan and is ducted around the engine nacelle to produce most of the thrust generated at takeoff. Core air is accelerated by the N1 fan, then enters the N2 core, where it is compressed, mixed with fuel, and ignited, and then it goes out as exhaust. So, that's the N1 and N2. The N1 fan is a single-stage fan that consists of 28 titanium alloy blades. Sometimes, depending on if maintenance has done maintenance on the blades, Like if there's a sharp edge, they'll shave it down to make it so it's a nice smooth edge. They'll number them. So you'll look up and you'll be like, oh, there's 16, 17, 18, 19. And you can only see like 5 or 10 or so. And you, oh, there's 16, 17, 18, 19, 20. Cool. They look good. A Kevlar blanket is wrapped around the fan housing to contain possible damage from a failed N1 fan. Fuel oil heat exchanger is used to warm the engine fuel and cool engine oil. Our limitation on engine fuel or on fuel is negative 30 degrees Celsius on the ground and negative 40 degrees Celsius in the air. And we get a caution message when the fuel temperature is like below 10. But that just, I mean, we just look at that and go, oh, well, we're still good. And wait a few minutes and the fuel will heat up. And everything's fine from there. So FADEC, we talked about that. One channel is in control, processing information to provide engine control outputs. The other channel operates in standby, so there's 2 channels. The in control and standby channels continuously share command and status data through crosstalk data bus. The FADEC has its own source of electrical power. Nothing really you need to understand. You need to know or understand about those 2 things, but just interesting information. We love redundancy in aviation, so each FADEC has many levels of system redundancy. And each message has a different impact upon the dispatchability of the aircraft. So this will go into now like maintenance requirements. So when you look at MEL, you'll see specific things. The category tells you how long that specific MEL can be on an airplane. And so for FADEC fault 1 status message, it can only be deferred for 10 days until maintenance has to go in and fix it. FADEC fault status 2 status message is a 30-day deferral. And then if it's just a FADEC caution message, no deferral. So depending on the message that shows up on the aircraft will depend on the deferral period and if it even can be deferred as well. There's some items on our status messages or on our caution that are no dispatch items. And so if we see one of those, a lot of times we reach out to you guys and say, hey, we got problems, or not to you guys, mostly maintenance, and say, hey, we can't go with this the way that it is. And then they'll help us run a fix. And the line maintenance dudes, they just defer. Like that's all that they do. They're always just trying to defer things. And yeah, so ideally that's just what they do. They want us to get back online and to keep going. So they just defer if they can. And if they can't, then they'll worry about fixing it and take the delay. With the thrust lever placed at idle, minimum N2 idle RPM is programmed in by the FADEC. And it takes in a bunch of information such as atmospheric, bleed air loading, and the phase of flight. So phase of flight, this just means that when we're on the ground just taxiing around, we are at true idle. Like we're burning as little fuel as possible. We're at true idle. When we're on final approach into landing, a lot of times the thrust is going to come up. Depending on how rough the conditions are, the thrust is going to be in and the thrust might be out. And just depending on how everything is working, this just tells us that while we're at the final approach phase, the phase of flight, when the thrust levers are idle, it's not going to be true idle. It's actually going to be spooled up a little bit. That way, if we do need to go around and we do need to throw that thrust up to get out of there, it's going to respond quicker. The 200 doesn't have that. So if you're at idle and you need to go around, it's going to take probably 3 or 4 seconds before you truly get the thrust required to start the go around. But the 700, it has it, so it's teed up. And the second that you say, okay, it's time to go, boom, it gives the thrust and you can get out of there pretty quick. FADEC will always program the best idle speed for any phase of flight, approach, landing, reverse, and ground. So FADEC's a pretty cool thing. Engine out. So when you lose one, FADEC computers automatically crosstalk to share data on the health of each engine. The FADEC will automatically increase the thrust on the operating engine when the other engine fails. And if the difference of N1 fan speeds exceed 15%, FADEC automatically increases the N1 speed of the operable engine. So yeah, it's just biggest thing to know is that FADEC is awesome, and it is a computer that is smart and helps when things go bad. APR, automatic performance reserve. I said power earlier. I lied. I'm sorry. It's automatic performance reserve. And it's available during normal or reduced takeoff or landing or go around phases. FADEC automatically computes a target thrust setting for selected thrust lever position, and it matches it. So you don't have to have the thrust levers like this. They can just be even, and it'll sync the N1 or N2, or it'll sync the N1 so that you're not hearing weird things or getting differential thrust. Okay, reduced. So we don't always want to be using full thrust to take off and land and things like that. So, especially take off. So a flex or reduced thrust is used when conditions allow. SkyWest has about 5 or 6 different conditions that they say you cannot use reduced thrust if there's wind shear, or if you're doing flaps in the 200, or there's a few other things. I forget them all. I know the acronym. We call it WATCH Flaps 8. But contaminated runways, tailwinds, things like that. But when we can, we like to, because it actually preserves the health of the engine and the life of the engine when you use a lower power setting to take off. And this is something that I find a little controversial, but the company wants you to do it, and they claim that the only engine failures that the company has had have happened at normal thrust takeoff settings. So they've yet to have an engine failure at reduced thrust. And I think that the engine was going to go out whether it was a normal or reduced thrust anyways. So I don't fully buy into that propaganda. Like, well, if it's flex thrust, you're not going to lose an engine. If those engines were still going to go, whether it was normal or reduced, in my opinion. So yeah, we like to do reduced. And what we do with that is we just put in a different temperature into the box. We trick the engine to saying it's a different temperature, meaning that it doesn't need as much thrust, and it'll compute down and not give as much thrust. In this one, the 200, the minimum reduced thrust setting is 83.5. There is no minimum reduced thrust setting for the N1 in the 700. Engine bleed air extract from the 6th or 10th stage of the engine compressor, normally provided from the 6th stage, right? We talked about that earlier. It uses the 6th stage first, and then if that's not enough, then it'll pull the 10th stage. Thrust lever settings, we talked about the detents: shut off, idle, climb, toggle, max power. Cruise setting is in the range in between idle and climb. Okay, thrust reversers. These help us slow down. Thrust reversers are awesome. They respond to electrical signals from FADEC and thrust reverse levers. The thrust levers are here, and then the reversers. So if you're at idle, you reach on top more, and then you'll grab these little levers. They have a locking mechanism. You grab the locking mechanism, pull it up, wait for them to arm, and then you stand them up, and that's full reverse. And it's accomplished by blocking and redirecting forward the fan bypass air. So pretty much blocks it, and as the engine is trying to propel it forward, it's actually pushing against itself, which is slowing it down. They're really efficient. They can really slow you down. So that's why when you land and you sometimes hear the engines go, whoop, yeah, they're reversing the thrust and really slowing us down. They're hydraulically actuated. And then this just, we talked about this when we talked about hydraulics. The left one is operated by or powered by hydraulic system 1. Right one is by hydraulic system 2. Water and wastes. Water systems store and supply potable water and lavatory wash water. Forward system for the galley. Aft is for the lav. And then the two systems are controlled from a single control panel located in the galley. Lavatory faucets, yeah. So I mean, it's just the galley water tank. It goes to the coffee pots and to the sink up, but we don't have a sink up front, so it's just the coffee maker. And lav, the aft one goes just to the sink and the lav. So that's it. Electric pump moves the water from the tanks, and then there's a way that you can drain it. Galley drain lines and overboard drain master heated. This still doesn't mean that it's like we can leave water overnight in a cold environment. And even the last few days in Chicago, it's been so cold that they will not fill the water. They won't have. They call it potable water. They don't have potable water. They won't fill the potable water just because it's been like 10 degrees Fahrenheit. So it'll freeze and damage the aircraft if they chose to do it, which hasn't been great. We bought a freeze dryer, and so I just freeze dry my meals. So I take little bags that they're like MREs, and I take my freeze dried meal, and I just a lot of times just use the hot water in the aircraft. But since they've not filled them up, I haven't been able to do that. So my last trip and probably this next one, I don't need as much. That's just because I have these nice containers, and if I can't get hot water to heat up the food, then I just wait till I get to the hotel and go get some from there. But anyways, that's my problem, not your problem. Cool. Water tanks are refilled and drained from 2 service panels on the right side of the fuselage. And this is the waste. The waste disposal system holds lavatory waste and provides a means for discarding waste materials. Draining, cleansing, rinsing, and pre-charging of the toilet holding tank is done from a service panel located on the right rear fuselage. You can also fill the system with blue juice, that's what we call it, by dumping blue juice into the toilet from the top. So you can either do it from the outside or you can just dump stuff in. Okay, cool. So that's the 700. We'll talk a little bit about the differences, and we've been talking about it the whole time. So most of this is going to be a review, but I'll let you know kind of the things that are super important. So it's different type certifications. The 700 has FADEC. The 200 has just those power plants. Just different engines. That's all that it is. This CRJ fuselage is 18.5 feet longer, 6.5 feet wider, and sits 3.5 feet taller than the Deuce. And we got both forward and aft cargo bay. In the 700, it has potentially up to 65 seats, I believe, maybe more if you. Oh, never mind. 70 seats. It can be up to a 70-seat configured aircraft. Most of our 700s have, or all of them have, a first class section in it. So that is what reduces the 70 to 65. However, it could have up to 70. And with that being the case, 2 flight attendants are now required. In the 200, there was only 1 flight attendant that was required since it's only 50 seats. So yeah, 2 are required in a 70 seat. If it's 51 seats, 2 are required. 50 or less, only 1. There are no autopilot differences. Flight director takeoff pitch information is enhanced and optimized. The 200, it's, yeah, once you take off, it's going to tell you information that's not true. It's going to have you try to pitch up to 15 degrees. And with a full boat, you will lose airspeed if you pitch up to 15 degrees. So whenever I talk to first officers that haven't flown the 200 in a while, I just say, listen, on rotation, 10 degrees. You go to 10 degrees, hold it, and then if you can see that the airspeed is still increasing, sure, go up to 12. And then if 12, you're still increasing, maybe go up to 15. But if that's the case, we are empty. We have nobody on the plane. Whereas the 700 will pitch up to 18 degrees and still be accelerating sometimes on takeoff, depending on how heavy we are. So the flight director is just more optimized and enhanced on this one. APU, it's located in the tail cone. The exhaust gases discharge rearward through the tail cone. The 200, they discharge underneath the right engine, and it's like, I'm 5'9", and it probably would hit me right above my ear. So yeah, there's definitely a danger area in the 200. No APU exhaust temperature hazard, and that's due to because it's 15 feet in the air, so it's not going to get anybody. Cool. Operating altitude 41,000 feet. APU start altitude 30,000 feet. Bleed air for ECS 25,000 feet, and bleed air for engine start 21. So these white numbers, those are the 700. These red numbers, those are the max for the 200. So it's better. At SkyWest, we actually don't go up to 41. Our max is a pilot limitation. It's 37,000 feet, and that's just because we don't have auto throttles. And with not having auto throttles, we have to pay attention to the thrust at all times. And we've had some pilots that have omitted it, haven't paid attention to the thrust, lost airspeed, and had some slow speed events at above 37,000 feet. And so since that's the case, they just said, nope, we're stopping at 37, and that's it. Bleed air for ECS. Oh yeah, it's fine. Fuel feed. The APU pump draws fuel from the left collector tank via the dedicated APU pump. No communication differences. Forward cargo bay door. We talked about that. That's the only difference for the doors. Fewer components, high related generators and transformer rectifier units, which is AC to DC power, and the level of automation operating limits. Generator ratings, this one's a big one. Max rating for generators, 40 kilovolt amps from 0 to 41,000. Max rating for the engine generators, 30 kilovolt amps from 0 to 35, and 25 kilovolt amps above 35. APU is 30. You got the AC power centers, no utility buses. DC power comes from the 4 TRUs and 2 batteries. I think in the Deuce there's 5 or 6 different TRUs. Oh, never mind. There you go. 5 TRUs and 2 batteries. So just one less transformer rectifier unit, which turns AC power to DC power. Cool. No DC differences. So 2 air conditioning system controllers, temperate regulation handled by each pack. So yeah, we got 2 system controllers rather. This one's just, it's more dinosaur-like. Recirculation fans, that's in the 700 only, and you can have the recirc fan turned on. It just circles there without having any packs on. Single, triple channel outflow safety valve, and then this one, the 200 only has 2 outflow safety valves. Maximum operation for single pack is 35, and the 200 it's 25. Those are things that you might need to know. So just with single pack, if you're down a pack, you can't fly as high. 31,000 is your limit. And then the consequences of that, not as much tailwind, more fuel thanks to the lower altitude, you're burning more. No jet pipe overheat warnings. That was in the 200, not in the 700. Engine pylon areas are monitored by anti-ice leak detection controller. And then the APU does not have a fire warning horn. Okay. Common halon extinguishing system consisting of 2 bottles is shared between both cargo bays. Both bottles discharge into the affected bay. So if it's a forward cargo issue, both of them go in there. If it's an aft, both of them go in there. One immediately and the one over the next hour. Yeah, differences are slats, rudder travel limiter, and multifunction spoilers. And then the multifunction spoilers replace independent spoilerons and flight spoilers on the Deuce. And the rudder travel limiter is installed to prevent pilot from overstressing the vertical stab. No flutter dampeners. The CRJ 200 is 2. Slats added to improve low speed handling. And the ISI is it's just prettier in the 700. The 200 is more round gauge, and the 700 is a nice screen with tapes and things. Oh yeah, I meant to talk about this. So the gravity refuel on the CRJ 700. So if you can't pressure refuel, the gravity refuel is 5,000 pounds less. It's 14,580 as opposed to 19,594. So it's a huge difference with how much you can take if you're doing a long flight. We looked at the fuel quantities. The crossflow system is simplified by using of a bidirectional pump. Fuel temperature is measured in the right wing tank instead of the left. It's similar. AC pump 1B and 2B do not load shed. Thrust reverser system in the 200 is powered by the 14th stage bleed air. In the 700, it's by hydraulic systems 1 and 2. Fourteenth stage bleeds supply for the air for the anti-ice in the 200, and in the 700, it's the 6th stage. And if the 6th isn't enough, it's the 6th and the 10th. Okay, ICAS control panel now installed in the center pedestal, different equipment cooling function. The nose gear doors of the 200 will always open to deploy and then close. And the 700, they're always open when the gear's down, and they're always closed when the gear's up. The 2 landing lights installed in the radome on the 200 and the single nose light on the nose strut. Photoluminescent tapes. And there's no navigation differences. The flight deck oxygen cylinder is installed behind the wardrobe in the flight deck, and in the 200, it's installed below the cabin floor on the forward right side of the fuselage. Okay, we talked about the pneumatics. The 6th first, and then the 10th. All aspects of bleed air management are now computer controlled, and there's always a leak detection system going on. Obviously, they have different engines. One is FADEC, the others don't. The thrust reversers are hydraulically powered. APR is available for a go-around. In addition to takeoff, that's on the 700. 200 does not have that. Thrust levers have no mechanical connection to the engines. The 200, they do, so they move really weird. The 700 is just a nice, smooth forward and back. And no wasting water, and that's it. Sweet. Good job. You made it through the systems. Before we go into the QRH procedures, does anybody want to talk about or have any questions with the systems?
One off-topic sort of question. Do you have auto throttles?
Not in the CRJ. No, there's some that have them, but SkyWest is too cheap. They didn't pay for them.
Bummer for you.
I know. I bet you feel so bad for me. It's a very big first world problem. I have to actually watch the airspeed and move the throttles if I'm going too slow or too fast. What? I have to fly the airplane? That's crazy. Yeah.
To turn a little knob.
Yeah, right. Exactly. So it's no problem at all. All right, so I'm gonna pull up the QRH for okay, so Gen 2, we'll look at that first. This is an abnormal. Gen 2 off. So I'm just gonna run you through the situation that I had going from Chicago to South Bend. So what happened was we were cruising, and then all of a sudden we got a message, Gen 2 off. And that message was associated, and there's two more that came with it, Mach trim and then yaw damp 2 and op. So you take those one at a time. I knew that the Mach trim was triggered by the Gen 2 coming off because sometimes the Mach trim disconnects due to the power or the power transfer, and so losing a generator was going to kick off the Mach trim. I kind of knew that. So for me, when I looked at it, I said, okay, first step, let's work on why the Mach trim disconnected, and that was because of the generator 2 going off. So generator 2 off. The QRH says Gen 2 off, reset, then on. So pretty much really simple. You turn it off, wait a sec, and you turn it back on. Okay, did it work? And then it says Gen 2 off, caution message persists. Yes, which is the case, it did. Then Gen 2 off, reset, and here it says the note. With Gen 2 shut down, hydraulic pump 1 Bravo is not available. During single generator operations, AC utility buses are load shed. Both battery chargers are not available. Okay, so we're not charging any batteries. We are just surviving on single gen operations. The next step, so this is what I did out of order. Again, I'm sorry. APU, if available at 30,000 feet and below, I was in the 200, start. So the APU is already going thanks to me just doing things out of order. The APU gen on. So this is so once the APU gen works, is going, you turn the APU gen on. Now you're back to 2 generators. Primary function of the APU is to back up the IDGs. When one fails, now you have that. And then it tells you to turn hydraulic pump 1 off. And that is because of the note saying that when the Gen 2 doesn't work, hydraulic pump 1 doesn't work, so shut it off. And then that is the end of that message. So that one was done. The next one that popped up was Mach trim. So we'll go find that one, and I'll show you how simple that one is. Let's see. Click that, search Mach trim. Okay, Mach trim, Abnorm 8-7. With at least one stab trim channel engaged, we had them both going. Mach trim engaged. To engage it, you press the button. That's it. No, with Mach trim, with a Mach trim failure, do not exceed 250 knots unless the autopilot is engaged and operating normally, which at the time it was not because it shut off. Once we got the second gen up, then it was operating normally again, so we were able to continue with that. Plus, we were at 8,000 feet, so we can't go faster than 250 knots anyways. You can't go faster than 250 until you're at 10,000 or above. And then the second note, 2 air data computers are required for Mach trim operation. So boom, that's it, done. Re-engage it, done. The next one was a yaw damp issue, and that is a status message. So it wasn't anything that we could do about it with the QRH. So I reached down, I clicked yaw damp 2, boom, thing worked again. That problem was fixed. And then we had one more message, and it was the IDG2. I think it just was IDG2. Yeah, Abnorm 6-17, IDG2. Gen 2 off reset, so we already did that, trying to fix it. With Gen 2 shut down, hydraulic pump 1B is not available. Already knew that. During single generator operations, both our AC utility buses are load shed. Both battery chargers not available. Already knew that. IDG2 disconnect, confirm, and disconnect. So it's a guarded switch in the air. We always confirm the guarded switches. So we said confirm. Both looked at it, made sure it's IDG2. Said sweet, pressed it, and then for no more than 3 seconds. And here's a note. If IDG2 status or disconnect status message is not displayed within 5 seconds, monitor oil pressure and oil temperature on the affected engine. The IDG cannot be reconnected during flight. That's why you confirm it, because it cannot be undone. APU, if available, at 30,000 feet and below, start. Again, did that out of order, my bad. APU gen on, hydraulic pump 1 off. And that's it. So you just run through those procedures, and then it will send out a message to dispatch saying, hey, we got problems. And then they'll say, cool. Well, good luck. We're cheering for you in the comfort of our comfy seat in St. George. We're cheering for you. So, all right. Well, I've taken you to the full time. Sorry about it. Does anybody have any questions or anything before you guys take off for the night? Okay, cool. Well, I'm gonna stick around until the last person's gone. So it was a pleasure. Good luck with everything. I'm happy for y'all. I hope everything goes smooth going through this 6 weeks and then the 2 weeks in person. So it was a pleasure. If you guys need anything, need my number, reach out to Jaden. He's got it. He can get it to you. And I'm excited to work with you in the future. Hopefully, all of you. So pleasure. Y'all take care. Have a great night. We'll see you around.
Appreciate it, Caleb.
Yeah, no
Stay
problem.
safe out there, man. Fly safe.
Appreciate that. Yeah, what's up, Noah?
I just had a random question. You said you flew DA-40s and Seminoles. Where did you go to flight school?
Utah Valley University.
Sweet. I'm a dispatcher there right now. I've been
Oh,
for a
that's
few
cool.
years. So just rang a bell in my head.
Yeah, yeah. I don't give great reviews about that plane.
Well, let's hear the tea. What'd you not like?
I just didn't like management. Initially, it was built way
Sure.
back when they were doing the best that they could to provide a good aviation experience at a budget.
Yeah.
And I'm going to stop recording this. That way I don't get in trouble. All right. Recording. Stop recording. Okay.